Imagine standing on a quiet shoreline at night. The sea is calm, the stars are faint, and the air feels almost too still. Out beyond the horizon, unseen by most, a colossal wave is racing forward. You cannot hear it yet, but you know it is coming. The strange thing is not the wave itself, it is the silence of the town behind you. No sirens, no warnings, no announcements, just business as usual, as though nothing unusual is rushing toward the coast. That image captures the feeling many scientists and independent observers describe when they talk about 3I divided by Atlas. Here we have an object that does not belong to our solar system, an interstellar traveler confirmed by orbital data approaching on a trajectory that places it within striking visual range of Mars in early October 2025. Its reality is undeniable. The paradox is the silence. Maximum drama in the heavens, maximum quiet on the ground. The discovery chain was not hidden. It began with faint, streak-like signals in late August, noticed first by small observatories in Europe and Asia. By September 3rd, independent confirmation solidified its identity, an interstellar body catalogued with the 3I designation that marks only the third confirmed visitor of its kind after Oumuamua and Borisov. That alone should have been headline news, an event so rare it belongs to a microscopic fraction of human astronomical experience. Yet the headlines never came. Instead, data circulated in astronomy forums, tucked into preprint papers, whispered across social media threads, where amateur skywatchers compared orbital fits. The information was there, but it moved through fragmented channels, technical language, and specialized plots. For the general public, it was as if nothing had happened. No press briefings, no panel discussions on major networks, no official voice saying, "Here is what we know, and here is why it matters." This is the essence of the paradox. We are not dealing with the absence of data. We are dealing with the absence of interpretation. The scientists who track Atlas are careful, even cautious, about what they publish. They prefer to wait for peer review, for confirmatory instruments, for follow-up observations. That caution is admirable. It is the backbone of science itself. But from the outside, to the ordinary viewer, it looks like silence. Into that silence pours speculation. Are governments deliberately suppressing the story? Are defense agencies classifying orbital data because of potential security implications? Or are the institutions simply paralyzed by their own protocols, waiting until they are sure before making any public declaration? Each possibility fuels further curiosity, and each week that passes without a clear official statement sharpens the sense of unease. On September 10th, the paradox intensified. A cluster of refined orbital calculations appeared on preprint servers, laying out Atlas's expected path with precision. A closest approach to Mars on October 3rd, a perihelion passage near the Sun by the end of October, and a return to observable range in December. These were not vague predictions. These were hard numbers, distances in astronomical units, velocities in kilometers per second, plotted with meticulous care. Anyone with the training to read them could see the implications. This object was not wandering, it was cutting a defined line through our neighborhood of the cosmos. Yet once again, no major agency convened a press conference. No reassuring statements appeared from national observatories. No televised Q&A gave the public a chance to ask what this meant. The silence deepened, and with it, the paradox grew louder. So, here we stand, in the opening act of Atlas's approach. On one side, a scientific drama of extraordinary magnitude is unfolding. A cosmic visitor accelerating past Mars, a rare interstellar messenger whose chemistry and trajectory may challenge what we think we know about comets and planetary systems. On the other side, the very governments and agencies we expect to lead the conversation remain mute. That is the tension that will frame everything we explore in this series, not just the object itself, but the silence surrounding it. And perhaps the most urgent question we can ask, the question that echoes through every forum and late-night conversation, is simple. Why are world governments silent about 3I divided by Atlas? Is this silence protection, paralysis, or strategy? The object is real, the silence is real, and together they create a mystery more compelling than either could be alone. When you step into the raw details, the silence becomes even stranger. By mid-September, Atlas had been logged not just in a single database but across multiple independent repositories. The Minor Planet Center listed its orbit. European observatories confirmed its trajectory. Spectrographic data trickled in from facilities in Chile and Hawaii. Each fragment of evidence was visible to anyone who knew where to look, and yet, outside those specialized circles, the event barely registered. For the average citizen checking the evening news, September 2025 looked like any other month. The paradox sharpened. Never before had so much information been technically public, and yet never before had so few people been aware of it. That gap between availability and accessibility is where the drama hides. Governments did not erase the data. They did not lock it behind firewalls. Instead, they allowed it to exist in silos too technical for most people to decode. It is a form of silence more subtle than censorship. Silence by complexity. A set of orbital elements posted on a server in Massachusetts is not the same as a televised briefing from NASA or ESA. To specialists, those numbers shout urgency. To everyone else, they are unreadable code. And so, while the professionals whisper to each other, the public continues unaware, lulled into calm by the absence of translation. The object moves forward through space, but the story stalls on Earth. Consider the timeline. On September 14th, independent astronomers in Japan shared high-resolution images showing Atlas brightening faster than expected. On September 18th, a European university preprint outlined unusual chemistry ratios in its coma. On September 21st, an American amateur network reported a sudden spike in visual magnitude. Each piece was striking. Each piece suggested Atlas was not just another comet, but something stranger, more volatile. Yet none of these reports reached mainstream platforms. There was no White House briefing, no European Space Agency press release, no coordinated response. Instead, what filtered through was scattered tweets, forum posts, and grainy telescope captures uploaded by night watchers. A cosmic messenger was screaming through the void, but the translation to human ears was faint and fragmented. The effect on public imagination was predictable. In the vacuum of official speech, speculation bloomed. Was Atlas on a collision course? Was it leaking exotic gases never before catalogued? Was it an interstellar fragment carrying unknown material? For every serious discussion in scientific circles, 10 threads were spinning wild theories online. And yet, even those wild threads circled back to the same core question. Why the silence? If this object is both real and extraordinary, why the reluctance to speak plainly about it? To some, silence meant danger. To others, it meant bureaucratic paralysis. To many, it was simply proof that institutions move too slowly for the rhythm of cosmic events. Here lies the deeper paradox. The object itself is not the only mystery. The greater mystery may be the behavior of our own systems of communication. Atlas exposes not just a gap in astronomy, but a gap in how scientific truth travels from observatory to living room. In earlier centuries, comets were seen by the naked eye, and their meaning was debated in public squares. Today, an interstellar comet can sweep through our neighborhood, documented by advanced telescopes, and remain invisible to public awareness. That silence is not empty. It carries weight, it shapes perception, and it fuels attention we cannot ignore. As Atlas moves closer to Mars in early October, that tension will only intensify. For if the silence holds, the dissonance between what is happening in the sky and what is being said on Earth may become as dramatic as the comet itself. By late September, the calendar itself had become part of the tension. The dates were not ambiguous. They were stamped clearly in every orbital projection. October 3rd, closest approach to Mars, a brush of 30 million kilometers cosmically close, astronomically significant. October 30th, perihelion, when Atlas would swing nearest to the Sun, briefly swallowed by glare, invisible to earthbound telescopes. December, re-emergence, when we would finally learn whether the object survived, fragmented, or transformed. These were the milestones, written not in rumor, but in hard celestial mechanics. They were the points that should have anchored public conversation, yet they passed with barely a ripple outside specialist circles. The Mars flyby on October 3rd was a moment that deserved attention. A third interstellar object in human history, cutting past another planet at a measurable distance, should have been the stuff of live coverage, countdowns, and public education. Imagine the chance to broadcast from the red planet's orbiters, to show the public real-time data as Atlas skimmed by. Yet there was no coordinated media push, no sense of spectacle. The data collected by Mars satellites was real, but it entered academic pipelines too slowly for the rhythm of public attention. For ordinary citizens, The day came and went without headlines. The cosmic drama unfolded in silence. Then came the greater silence, perihelion. On October 30th, Atlas slid behind the glare of the sun from Earth's perspective, hidden in brilliance. Astronomers call this a blackout window, a natural consequence of geometry, not conspiracy. Still, in public imagination, it felt symbolic. At the moment of maximum intensity, the object disappeared, and the institutions remained mute. It was as if the universe itself had conspired to deepen the mystery. For weeks afterward, there would be no direct visual confirmation. Only models, extrapolations, and speculation filled the gap. Would Atlas survive the heat? Would it fracture into dust? Would its chemistry change in ways that redefined our theories of interstellar bodies? Each question hung unanswered, suspended in silence. The irony is painful. Atlas offered one of the most extraordinary opportunities in planetary science in decades, and yet the narrative that reached ordinary people was not discovery but absence. Silence became the story. This is the paradox in its sharpest form. At the very moments when communication should have been clearest, when the public most needed to know what was happening, the voices of authority receded. The comet burned across the void, Mars orbiters took their readings, the sun's glare swallowed the object, and the only thing most of the world heard was nothing at all. The drama was maximum, the noise was minimal, and so the question hardened into something sharper than curiosity. Was this silence incompetence, indifference, or intent? Whatever the explanation, October's twin milestones underscored the stakes. Atlas was not simply a distant light in the night sky. It was a test of how our species handles the extraordinary. Do we share it, explain it, invite the public into the wonder? Or do we retreat into technical circles, letting silence define the narrative? The comet itself is a messenger from beyond the stars, indifferent to our debates. But our response to it reveals something about us, our institutions, our priorities, our trust in transparency. October 2025 may be remembered not only for what Atlas did in the sky, but for what our governments chose not to say on the ground. And as the calendar turned toward December, one truth remained. The silence was now inseparable from the story. Silence is not neutral. In the case of 3I divided by Atlas, silence becomes an active force, shaping how people think, speculate, and respond. For the trained eye, the orbital data tells a clear story. An interstellar traveler, swift and unique, cutting through the solar system with mathematical precision. But for the public, deprived of context, what remains is only the drama of absence. Every unspoken word becomes fuel for imagination. Every missing briefing becomes a symbol of concealment. Silence amplifies fear as much as it amplifies awe. In the paradox of Atlas, the quiet may be more powerful than the comet itself. Think of how societies once reacted to celestial events. When a comet blazed across ancient skies, entire civilizations debated its meaning in open plazas. The light was visible to everyone, and its interpretation became a shared experience, sometimes terrifying, sometimes inspiring, but never hidden. Now, in the 21st century, a comet from beyond the stars passes closer to Mars than any interstellar body before it, and the public conversation is muted. The eyes that see it are few, the words that describe it are fewer, and the voices of authority are almost absent. It is a strange inversion of progress. More technology, more data, more telescopes than ever before, yet less collective awareness. The cosmic drama is louder than anything our ancestors could have imagined, but the cultural noise is almost zero. This is where the paradox deepens. Silence not only conceals facts, it also alters trust. Each day without official acknowledgement makes institutions look weaker, more distant, and less responsive. Citizens ask, if this is extraordinary and benign, why not explain it? If it carries risks, why not prepare us? The longer the pause, the more corrosive the effect. Silence breeds conspiracy as naturally as a comet breeds a tale. Into the vacuum rush, questions about secrecy, defense briefings, even wild speculations about alien craft. None of those theories is grounded in evidence, but evidence is not what thrives in silence. Narrative does. And so, the paradox of Atlas is not just scientific, it is psychological, political, even cultural. The comet itself cannot speak. It burns, it arcs, it follows gravity's pull. The silence is ours. It belongs to our governments, our institutions, our decision to say nothing at the very moment something deserves to be said. That choice will echo long after Atlas swings back into the outer dark. In December, when it re-emerges from behind the sun and telescopes capture its altered face, we may learn more about its composition, its survival, and its meaning for planetary science. But what will linger is not just the data. What will linger is the memory of silence. Generations may look back and ask not only, what was Atlas? But also, why did no one tell us in time? And so, as we close this opening act, we arrive at the heart of the paradox. Maximum drama above, minimum noise below. Atlas is real, spectacular, and demanding of attention. Governments are silent, restrained, or deliberately cautious. Between those two realities lies the mystery that drives this investigation. To understand it, we must move beyond the silence and examine the fragments of truth already scattered in the record. Because even in the quiet, the data exists hidden in preprints, buried in orbital charts, whispered in small observatories. Our task now is to pull those fragments into focus, to see what they reveal, and to test whether the silence hides ignorance, caution, or something more. The comet is moving forward. So must we. The data is not missing. It exists, piled up in archives, posted on servers, whispered across astronomy forums, and logged in databases that anyone can technically access. And yet, for the public, it might as well be missing. That is the first paradox of 3 I divided by Atlas, after its formal confirmation in September 2025. We know more about this interstellar object than any comet tracked in the past decade. Its orbital elements have been calculated, its composition sampled, its magnitude recorded night after night. But the knowledge is scattered, fragmented, like shards of glass across different rooms of the same house, each piece sharp but incomplete, almost impossible to piece together into a coherent picture. For the expert, the shards shine. For the layperson, they cut. And so the object grows brighter in the sky while its meaning remains dim on Earth. Take the designation itself. On September 2nd, the Minor Planet Center stamped Atlas with its formal identity, 3I divided by C divided by 2025 N1. In a single code, centuries of astronomical convention crystallized. 3I, the third interstellar object ever confirmed, following Oumuamua in 2017 and Borisov in 2019. C, a cometary body, not a mere asteroid. 2025 N1, a timestamp of its discovery sequence. For those who live inside the world of orbital dynamics, this code was explosive, a headline compressed into 12 characters. For the public, it was meaningless. News outlets did not translate it, agencies did not broadcast it, and the string of symbols slipped past like a secret handshake in a language most people never learned. The first crack in the record was already there, the gap between existence and comprehension. 4 days later, the orbital refinements were posted. Atlas was found to be retrograde, moving against the normal planetary flow but only 5 degrees off the ecliptic plane. To specialists, this geometry was extraordinary. It meant Atlas would skim through the solar system on a path unusually aligned with the planets, maximizing its visibility, interaction, and observational potential. In terms of celestial mechanics, it was like watching a visitor merge onto the busiest highway in space, driving in the opposite direction but staying close to the lanes. For the few who understood orbital plots, it was thrilling. For the rest of the world, it was invisible. No agency stepped forward to translate the drama. The numbers remained numbers, trapped in diagrams only insiders could decode. Then came the chemistry. On September 12th, an independent observatory in South America uploaded preliminary spectrographic data. The results were stark. Carbon dioxide emissions were nearly 8 times stronger than water vapor. Such a ratio is unheard of in solar system comets, where water typically dominates. For planetary scientists, it was a revelation. Atlas was not only interstellar, it was chemically alien. It challenged assumptions about cometary formation, planetary migration, and the distribution of volatiles across galaxies. But the paper that carried this bombshell was tucked into a technical archive, wrapped in equations, uncertainty intervals, and acronyms. To anyone outside the narrow circle of professionals, it was unreadable. The fact existed. The narrative did not. The pattern repeated. On September 14th, Japanese astronomers released high-resolution imagery showing Atlas brightening faster than predictions suggested. On September 18th, a European preprint reported anomalies in the light curve, including unexplained fluctuations in brightness over short timescales. On September 21st, an American amateur network noted a sudden spike in apparent magnitude, consistent with outbursts of gas or dust. Each of these observations added depth to the picture. Each was a receipt of reality, but each was confined to niche platforms, preprint servers, or hobbyist mailing lists. None reached the public in forms they could grasp. No major agency synthesized the findings into a story. No institution took the shards of glass and assembled them into a window. Instead, the cracks widened. For the public, this silence felt like suppression. But the truth was subtler and perhaps more frustrating. The data was public, but not public-facing. It was present, but inaccessible. It was technically open, but practically closed. This is a silence not of censorship but of opacity. A kind of silence that arises when institutions mistake availability for clarity, when they believe that posting raw numbers is the same as communicating meaning. Atlas revealed this flaw like an X-ray, the gap between knowing and telling. That gap is the true crack in the record, and as long as it persists, the object will remain both the most documented comet in history and, paradoxically, the least understood by the very people it should matter to most. If the first crack in the record is the gap between data and comprehension, the second crack is the way that data is scattered. It is not just one missing press conference. It is dozens of small silos, each holding a piece of Atlas, none designed for the public eye. The Minor Planet Center keeps orbital elements in dry tables. Preprint servers host chemistry results in PDF files laden with jargon. Observatory websites post nightly magnitude readings without explanation. Amateur astronomers scatter their images across forums and social media. Each fragment is real, but the mosaic never assembles itself. To anyone outside the inner circles, the object dissolves into noise, sharp facts without story, receipts without translation. And that silence, paradoxically, becomes louder the more pieces exist. Consider what an ordinary citizen encounters. They open a newsfeed in late September. They see almost nothing about Atlas. If they dig further, perhaps they stumble across a tweet from an astronomy forum, linking to a preprint that mentions unusual CO2 ratios. But the file is dense, unreadable, and stripped of context. Without training, they cannot parse whether the numbers signal danger, discovery, or simple curiosity. If they try another source, they might find an orbital chart published in a format only specialists understand: right ascensions, declinations, perihelion distances in astronomical units. For an expert, it is straightforward. For the layperson, it is gibberish. The silence is not absolute, but it is functionally the same. What is visible is not comprehensible, and what is comprehensible is not visible. Even within the scientific community, the fragmentation creates delays. A team in Japan posts images of Atlas brightening. Days later, a European group releases a different set of data showing brightness fluctuations. Meanwhile, an American amateur collective notes a sudden outburst. Each group is correct in isolation, but because their findings do not converge into one synthesized report, the overall picture lags behind the pace of events. By the time a clear consensus begins to emerge, the comet has already moved on, leaving behind confusion. The silence is not only between institutions and the public, it is also between the institutions themselves. This is the part that feels quietly infuriating. It is not that governments or agencies are deliberately hiding Atlas. It is that they are failing to coordinate, failing to communicate, and failing to treat the event as extraordinary in real time. In an age when news cycles run by the minute and rumors can reach millions within hours, the old model of waiting months for peer review feels painfully inadequate. Atlas is moving at 60 kilometers per second. Peer review is moving at walking speed. The mismatch is almost absurd, and in that mismatch, public trust erodes. People sense that something is happening, but the story they receive is incoherent. They call it silence because silence is what incoherence feels like. Think about how this contrasts with other global events. A volcanic eruption triggers immediate briefings. An earthquake produces instant updates. Even a solar flare sparks quick headlines about potential impacts on satellites. Yet an interstellar comet, rarer than all of those combined, slips past almost unnoticed. Why? Because, unlike volcanoes, earthquakes, or flares, Atlas does not fit neatly into the templates of crisis communication. It is not an immediate threat. It is not easily explained. It is not even visible to the naked eye. And so, in the bureaucratic calculus of what deserves attention, Atlas is pushed aside. The silence is not malicious, but it is structural. It grows out of habits of caution, habits of delay, habits of treating science as something that can wait. But Atlas does not wait. It does not pause for institutions to catch up. It does not care about peer review or press briefings. It accelerates, brightens, and evolves, whether or not anyone is ready to talk about it. That is the lesson buried in these cracks. Information without narrative is not communication. Facts without synthesis are not knowledge. And as long as those cracks remain, Atlas will continue to exist in two parallel worlds, one where specialists track every kilometer of its path, and one where the public hears almost nothing at all. When silence fills the space where clarity should live, people do not remain quiet. They speculate. They create their own bridges between fragments, often with materials more imaginative than factual. That is exactly what happened in the weeks after Atlas's confirmation. Across social media, forums, and podcasts, the absence of accessible narrative was replaced with a flood of alternative ones. Some argued that Atlas was on a collision course with Mars, and that agencies were deliberately concealing the threat to avoid panic. Others insisted the comet's unusual chemistry, those abnormal carbon dioxide ratios, was evidence of something artificial, perhaps even technological. A smaller but louder minority spun fantasies of Atlas as a harbinger of cosmic prophecy, a sign that governments were secretly preparing for contact. None of these claims had evidence. All of them had traction. Why? Because silence breeds narrative, and in the vacuum of institutional voice, speculation becomes irresistible. This is not new. History shows us that uncertainty in the sky always spills into culture. Medieval comets inspired apocalyptic sermons. 19th century eclipses were tied to superstition. Even in the 20th century, UFO sightings flourished whenever the official record was thin. The pattern is stable. The less clarity authorities provide, the more creativity ordinary people apply. The difference today is scale. In 2025, a single speculative thread can reach millions overnight. A half-understood screenshot of orbital data can ricochet through platforms, stripped of context, repurposed as evidence for whatever story a creator wants to tell. And because the real information is hidden in PDFs, arcane charts, or paywalled journals, it cannot compete. The noise wins by default. This does not mean the public is irrational. In fact, the opposite may be true. The instinct to fill silence with story is profoundly human. People want coherence. They want meaning. When official channels fail to provide it, they build their own. The frustration, then, is not that the public speculates, it is that institutions leave them no other choice. A comet traveling 60 kilometers per second through the inner solar system is not an ordinary event. The public deserves more than silence. When silence is all they receive, distrust deepens. And once distrust sets in, even genuine updates when they finally arrive are treated with suspicion. That is the cost of waiting too long to speak. Atlas makes this dynamic painfully clear. On September 20th, a citizen science group released telescope images showing a sudden brightening. Within hours, threads appeared, claiming it was evidence of an imminent outburst or even a fragmentation event. The actual scientists, who understood the variability of cometary light curves, stayed quiet, waiting for confirmation. In that pause, the wildest theories spread unchecked. A week later, the European data suggesting anomalous brightness fluctuations was posted. To experts, this explained the brightening as normal instability. But by then, the narrative was set. For much of the online public, the brightening remained proof of hidden danger. Silence had allowed speculation to root itself deeper than any later correction could reach. The irony is sharp. The data is there. The professionals are cautious. The institutions are silent. And so the object that could have unified wonder instead divides perception. Specialists see opportunity, a unique chance to study interstellar chemistry. The public sees secrecy, another instance of being left in the dark. Both views grow from the same source, but they diverge into different realities. That divergence is itself a crack, one that threatens to grow wider with every week of delay. The longer Atlas streaks silently through the sky, the harder it will be to close that gap. And the public's growing sense of exclusion may prove as consequential as any scientific discovery the comet delivers. The cracks in the record are frustrating, but they are not empty. Inside those fractures lie receipts small, verifiable, undeniable. They may be scattered, but they are real. If we step back and look at them together, even in their fragmented state, they tell us something important. Atlas exists. Atlas is unusual, and Atlas is worth attention. The challenge is not the absence of proof, but the absence of cohesion. The comet story is not hidden. It is simply written in pieces, scattered across too many ledgers. To read it, you must assemble it like a puzzle with missing edges. The frustration is that no official hand offers to help. And yet, the pieces themselves are enough to sketch an outline of truth. Look again at the timeline. September 2nd. Designation as 3I divided by C divided by 2025, N1. Confirmation that this was no ordinary comet but the third interstellar object ever logged. September 6. Orbital refinements showing a retrograde path within 5 degrees of the ecliptic plane. Unusual geometry that increases both its visibility and significance. September 12th. Spectroscopic readings revealing an alien chemistry dominated by carbon dioxide. September 14th. Independent imagery, confirming a faster than expected brightening. September 18th. A preprint reporting anomalous light curve fluctuations. September 20th. Citizen science, observations of sudden magnitude spikes. Each of these is a receipt. Each of them anchors Atlas in reality. Together, they form a record more compelling than rumor and more reliable than speculation. The problem is not the data itself. The problem is how fractured the record appears when left unsynthesized. This fracture, however, is precisely why Atlas feels so elusive. A public looking for coherence instead sees contradiction. One group says brightening, another says fluctuation, another says outburst. Without context, these appear to clash. With context, they converge. A volatile interstellar comet undergoing natural instability as it approaches the Sunday. But because no central voice explains the coherence, the fragments remain shards. The silence of authority turns receipts into riddles. The data is technically public but practically inaccessible. And so the cracks widen not because Atlas is unknowable, but because the process of knowing is left unspoken. Yet if we resist frustration for a moment, there is something profound in this very messiness. Atlas shows us not only the limits of communication, but also the resilience of evidence. Even when scattered, the receipts survive. Even when ignored, the data accumulates. Even when mistranslated, the numbers remain what they are. This is what makes science distinct from rumor. Facts may be fragmented, but they do not vanish. They wait to be assembled. The cracks in the record are not the same as the absence of a record. They are an invitation to look harder, to connect, to test. That is where we stand at the close of this section. We know Atlas is real. We know its path is interstellar. We know its chemistry is strange. We know it has brightened, fluctuated, and startled observers across the world. We also know that governments have not told this story clearly, and that silence has bred distrust. These are the cracks, a record full of receipts but short on translation. The task before us is to follow the evidence across those cracks, to piece together the puzzle until a picture emerges. Because even in fragments, the picture points to anomalies that cannot be ignored, and it is to those anomalies, the unexpected chemistry, the unstable behavior that we must now turn. Atlas is not only silent in the mouths of institutions, it is also loud in the data itself. The question is whether we are willing to listen to the fragments long enough to hear the whole. Imagine a comet that breathes not water but carbon dioxide, not the familiar steam of melting ice, but the sharp hiss of dry ice venting into space. That is 3I divided by Atlas. In mid-September 2025, spectroscopic data revealed something extraordinary. The gas cloud around Atlas contained nearly 8 times more carbon dioxide than water vapor. To put that in perspective, most comets in our solar system carry the opposite signature: water dominates, while CO2 plays a secondary role. Atlas inverts that pattern completely. It is as if you opened a soda can expecting fizz, but instead were hit with the blast of a fire extinguisher. The chemistry is alien, the ratios defy expectation, and the discovery leaves scientists both fascinated and unsettled. Why does this matter? Because comets are more than chunks of rock and ice. They are archives of origin, frozen records of the environments in which they formed. In our solar system, comets preserve the fingerprint of early planetary chemistry. Their water-dominated outgassing tells us they were born in regions where water ice was abundant and stable. Atlas, by contrast, whispers of a birthplace where carbon dioxide reigned, where conditions were so different that CO2 became the primary volatile. That birthplace was not here. It lies somewhere beyond our star, perhaps in another system altogether, shaped by rules we have not yet experienced. Atlas does not just travel from beyond, it carries beyond within it. The numbers are not vague. On September 12th, an observatory in Chile posted raw spectra to a public archive. Independent teams in Europe cross-checked the data within days. The signal was clear. Deep absorption features at wavelengths corresponding to CO2, far stronger than any waterline. The ratio was approximately 8:1. To a planetary scientist, this is astonishing. It would be like finding an ocean on Earth where salt outweighs water, or an atmosphere where oxygen is just a trace gas compared to something exotic. Such chemistry is not only strange, it is destabilizing. It tells us that the diversity of planetary systems is broader than our models predict. It tells us that life in the cosmos may encounter building blocks far different from the ones we know. And then comes the unsettling part. This anomaly is not static. Atlas's outgassing does not behave in steady, predictable patterns. On some nights, the CO2 signature flares, spiking in intensity. On others, it dims, as if the comet exhales irregularly. This variability confuses models and frustrates predictions. Is the nucleus layered, with CO2-rich regions exposed unevenly? Is sunlight triggering pockets of gas that burst like geysers? No one knows for sure. What we do know is that Atlas refuses to behave like a normal comet. It flickers, surges, quiets, then flares again. It is alive with instability, like a heart that refuses to settle into rhythm, and watching that heartbeat from across millions of kilometers fills observers with both wonder and unease. This is where the feeling shifts. We are not only dealing with data, we are confronting the unfamiliar. To speak of Atlas is to step into a realm where our solar system is no longer the template, where even the basic chemistry of comets is upended. It is a reminder that the universe is not obliged to follow the rules we grew up with. That realization is exhilarating, but it is also humbling. For if Atlas carries the fingerprint of a foreign system, then every vent of CO2 is a message from elsewhere, a chemical postcard from a world we cannot see. The question is whether we are prepared to read it. If Atlas's chemistry feels alien, its behavior makes the case even stronger. Comets, in theory, are supposed to be predictable in how they brighten as they near the sunday. Heat drives sublimation, sublimation releases gas and dust, and brightness increases in a curve that astronomers can model with reasonable accuracy. But Atlas does not respect that script. Its light curve is jagged, volatile, unpredictable. In mid-September 2025, within a 48-hour window, Atlas brightened by almost a full magnitude, an enormous leap, only to dim again within days. Imagine a light bulb flickering on a faulty wire, sparks of brilliance followed by sudden weakness. That is Atlas, not a steady lamp in the sky, but a nervous flame in constant motion. For seasoned comet watchers, this volatility is both exciting and unnerving. Exciting because it suggests complexity, unnerving because it resists explanation. Among the strangest features was the appearance of a sunward plume. Normally, a comet grows a tail that streams away from the sun, shaped by solar radiation and the solar wind. It is one of the most basic rules of comet behavior, so ingrained that it is drawn in every children's book illustration of the solar system. But in early October, telescopes captured Atlas doing the opposite, releasing a plume of material pointing toward the sunday. It was faint but clear, a reversal of expectations. For astronomers, this raised urgent questions. Was Atlas venting large, heavy particles that the solar wind could not push outward? Were internal jets blasting at odd angles, overriding the normal dynamics? Or was there something unique about the comet's dust that made it interact differently with sunlight? No matter the answer, the very sight of a comet pushing back against the sun was breathtaking. To some, it looked like defiance, as if Atlas were unwilling to follow the same physics that govern every other comet. The erratic outbursts compounded the puzzle. Amateur astronomers across North America and Europe reported sudden spikes in brightness on September 20th and again on the 23rd. These outbursts were short-lived but dramatic, suggesting mini-explosions on the comet's surface. Theories multiplied. Perhaps pockets of gas beneath the crust built up pressure until they burst like geysers. Perhaps volatile ices other than water, carbon monoxide or methane, were embedded in layers that released unpredictably. Some even wondered if the nucleus was fragmenting, with chunks breaking away and briefly reflecting sunlight before dissipating. None of these scenarios was proven, but each underscored the same truth. Atlas was not calm. It was active, unstable, restless. Observing it was like watching a living system breathe in chaotic rhythm, its pulse irregular and untrustworthy. Why should this matter? Because the way a comet behaves reveals what it is made of and how it is built. A stable comet implies a homogeneous nucleus, a structure where ices and dust are evenly distributed. An unstable comet implies complexity, stratified layers, trapped gases, and weak surfaces that collapse under stress. For scientists, Atlas's behavior is a goldmine. Each plume, each flicker, each unpredictable outburst is a clue to the architecture of a body formed in another star's nursery. For the public, the spectacle is harder to parse. To many, it looks like Atlas has moods, like it is alive in some symbolic way. Of course, scientists do not claim sentience, but the language of behavior flickering, outbursting, defying, makes it hard to avoid the impression of vitality. And in that impression lies awe, mixed with unease. There is also a deeper lesson. Humanity has grown comfortable with the idea that the heavens can be calculated. We pride ourselves on knowing when an eclipse will occur a century from now, when an asteroid will cross Earth's orbit in the next millennium. Atlas shakes that comfort. It reminds us that prediction has limits, that the universe still holds surprises too volatile for equations to capture fully. A comet brightening and dimming like a faulty star, sending plumes toward the sun, is a reminder of humility. It is proof that the cosmos is not fully domesticated by human models. Atlas's behavior is not just a curiosity, it is a humbling confrontation with the unknown. For every scientist tracking its light curve, there is a moment of wonder. For every member of the public who glimpses its images online, there is a flicker of awe mixed with the quiet recognition that the sky still belongs, in part, to mystery. The more Atlas misbehaves, the more theories multiply. Scientists are cautious with words, but behind the caution is a restless curiosity. How do you explain a comet that breathes carbon dioxide, brightens unpredictably, and throws plumes toward the sun? No single model fits perfectly, but several working hypotheses have emerged. Each is a glimpse into possible architectures we have never directly observed, each carrying implications that stretch beyond Atlas itself. The first and most popular hypothesis is the layered nucleus. Imagine a cake baked in another kitchen of the galaxy, with alternating layers of ingredients. In this case, the outer shell of Atlas could be rich in carbon dioxide, exposed first as sunlight strikes. Beneath that crust may lie layers of water ice, hidden for now but waiting to sublimate as Atlas swings closer to the sunday. If true, we might expect Atlas's chemical signature to shift after perihelion, dropping from an 8:1 CO2 to H2O ratio towards something more balanced. Scientists will be watching carefully in December, once the blackout ends, to see if the spectrum evolves. If it does, the layered model gains strength. If it doesn't, the mystery deepens. Either way, the comet is telling us about its birthplace, a region where volatiles condensed in a pattern alien to our solar system. A second hypothesis centers on pressure pockets. Comets are not solid stones but porous, fragile assemblies of ice and dust. It is possible that Atlas's interior hides sealed cavities of gas, trapped for eons. When sunlight penetrates just enough, these pockets burst, releasing sudden jets that spike the comet's brightness. This could explain the erratic outbursts reported in September. It would also account for the sunward plume. If the venting happened to erupt from a surface facing the sun, the plume would naturally point that way, defying the textbook comet tail. This model is compelling because it matches what we know about porous bodies, yet it feels unsettling. It suggests Atlas is a ticking engine of random bursts, a body that hides pressures waiting to explode without warning. The thought of such ancient volatility reaching our solar system is both thrilling and humbling. A third line of thinking focuses on the dust itself. Not all cometary particles are created equal. Fine grains are pushed easily by sunlight, but larger clumps resist, sometimes even moving in counterintuitive directions. If Atlas's nucleus is shedding unusually large grains, that could produce the sunward plume effect, heavy particles falling toward the sun under gravity rather than being swept away by radiation. This idea reframes Atlas, less as a rebel and more as a supplier of exotic dust. Yet it still leaves open questions. Why so much large dust? Why now? What does it imply about the comet's structure? The answers remain elusive, and the hypotheses remain parallel rather than convergent. Comparisons sharpen the strangeness. Borisov, the second interstellar comet, behaved in many ways like a normal solar system comet, dusty, volatile, but chemically familiar. Oumuamua, the first interstellar object, was stranger. No clear coma, an odd acceleration, sparking debates about radiation pressure or even artificial origin. Atlas seems to combine the alien chemistry of Oumuamua with the cometary volatility of Borisov, as if the universe were reminding us that each visitor can break a different rule. It is a sobering lesson. There is no template for interstellar objects, no standard manual to read. Each one rewrites the boundaries of what we thought we knew. For the public, these hypotheses may feel abstract, but they are the heartbeat of science. They show that even in the face of anomalies, there is method, there is structure, there is curiosity disciplined by evidence. At the same time, they remind us that our models are provisional, always one comet away from being rewritten. And in that reminder lies a quiet awe. Atlas is not just a puzzle, it is a mirror, reflecting our hunger to understand and our humility in the face of the unknown. Picture a car entering a busy highway in the wrong direction. The lanes are filled with traffic moving fast, each vehicle locked into the same flow. Suddenly, headlights appear against the stream. The car doesn't crawl on the shoulder or spin in confusion. It merges directly into the oncoming lanes, threading itself into the thickest part of the current, daring every driver to adjust. That is the image astronomers use when describing the orbit of 3I divided by Atlas. Unlike the thousands of comets born in our solar system, which travel broadly in the same direction as the planets, Atlas charges the other way. It is retrograde, yet what makes this geometry extraordinary is not only its direction, but its alignment. Atlas runs almost perfectly along the ecliptic plane, the very flat disk where Earth, Mars, and nearly every other planet trace their paths around the Sunday. It is as though the intruder chose not only to enter the wrong way, but to do so in the most crowded lane available. For anyone hearing this for the first time, the temptation to speak of intent is overwhelming. Surely a body from another star could not just stumble into our planetary highway so precisely. And yet, science requires that we resist that temptation. Geometry is not intention, and the moment we confuse the two, we abandon evidence for narrative. The details are striking enough without exaggeration. Orbital refinements on September 6th placed Atlas on a path tilted less than 5 degrees from the ecliptic plane. That is almost flat by astronomical standards. When it swept past Mars on October 3rd, its distance was just 0.19 astronomical units, close enough for orbiters to collect valuable data, but far outside any risk zone. Its perihelion on October 30th brought it to 1.4 AU from the Sun between Earth and Mars in distance, still hugging the planetary sheet of motion. For context, most comets approach at inclinations far greater, often 20, 30, or even 90 degrees, diving in and out of the solar system, like needles stitching through cloth. Atlas, by contrast, skates along the fabric itself, a thread woven in reverse. Rare? Absolutely. Impossible? No. The cosmos allows infinite approach vectors, and some will inevitably line up in ways that feel uncanny. To treat that rarity as evidence of purpose is to mistake surprise for signal. The comparison with previous interstellar visitors sharpens the picture. Oumuamua, the first, entered at a steep angle and zipped through quickly, barely leaving time for telescopes to react. Borisov, the second, was more conventional in behavior, a comet with dust and water signatures, tilted enough from the ecliptic to avoid metaphor. Atlas is different. Its alignment is tighter, its retrograde motion more visually dramatic. For the human mind, trained to see stories in patterns, the instinct is clear. It looks intentional. But this is where selection bias creeps in. We remember the rare alignments, the ones that feel meaningful, and forget the countless ordinary ones that did not. Out of all the possible interstellar paths that never cross our attention, we focus only on the ones that do. Atlas is not sending a message, we are projecting one. And yet, even stripped of speculation, the geometry is a gift. Because Atlas skims the ecliptic, our telescopes and spacecraft already aligned with the same plane can observe it continuously without awkward repositioning. Its retrograde speed relative to planetary motion sharpens our measurements, providing higher resolution in spectra and particle analysis. What looks like intent to the layperson looks like opportunity to the scientist. Atlas is unusual, yes, but unusual is what makes it valuable. It is the exception that tests our models, the outlier that stretches our understanding. To frame its trajectory as deliberate is to indulge the imagination. To frame it as chance aligned with fortune is to honor the evidence. And in this case, honoring the evidence is no less dramatic. It is more. For the drama lies not in secret intention, but in the sheer improbability of natural chance carving such a path. What makes Atlas so irresistible to the imagination is not only that it is retrograde, but that it is almost eerily well aligned with the solar system's main plane. From Earth's vantage point, its orbit looks less like a random intrusion and more like a calculated thread woven through familiar lanes. In September, when orbital refinements sharpened, astronomers realized the comet's path crossed within a hair's breadth of planetary orbits. Mars in early October, Earth's neighborhood a few weeks later, Jupiter's outer reach further down the line. None of these passes carried collision risk, but their geometry was close enough to stir unease. To a casual observer, it looks like aiming. To a scientist, it looks like statistics. The difference between those two perspectives is vast, and it is the difference between story and science. Take the Mars flyby on October 3rd. Atlas passed at 0.19 astronomical units, around 30 million kilometers. On the scale of the cosmos, that is practically side by side. To a public used to kilometers and miles, it sounds terrifyingly close. To astronomers, it is safe by many orders of magnitude. Yet headlines of near miss began circulating online, fueled by the visual of an interstellar visitor brushing Mars's orbital lane. The truth is that Mars was never in danger, and Atlas's trajectory was always transparent. But because the orbit hugged the ecliptic, the visual overlap felt meaningful. That feeling was an illusion, not evidence. Still, it was powerful enough to convince thousands that intent was at play. This instinct to project meaning onto geometry is deeply human. We evolved to detect patterns, faces in clouds, constellations in stars, purpose in coincidence. A comet threading the planetary plane invites the same projection. The orbit looks neat, precise, deliberate. But probability ensures that out of countless random interstellar approaches, some will appear this way. The key word is appear. Atlas's trajectory is not evidence of control. It is evidence of chance creating shapes that our minds are primed to interpret as purpose. This is the essence of selection bias. We remember the rare alignments that look extraordinary and forget the countless trajectories that looked unremarkable. Atlas is memorable precisely because it excites our bias, not because it carries intention. To see this more clearly, imagine flipping a coin 1,000 times. By chance, you will sometimes get 10 heads in a row. When that streak appears, it feels uncanny, even magical, but mathematics insists it must happen eventually. Atlas's orbit is our streak of heads. It looks special because it is unusual, but unusual does not mean intentional. It means that, in a vast universe with billions of random vectors, one of them was bound to align in a way that would catch our attention. We notice Atlas not because it proves design, but because our attention is wired to notice it. The irony is that in resisting speculation, scientists find greater wonder than any conspiracy could offer. To them, Atlas's low inclination is not a hint of alien steering but an observational gift. Its alignment makes it easier to track with instruments already pointed along the ecliptic. Its retrograde velocity increases the relative speeds of particles and photons, sharpening spectroscopic measurements. The very features that look suspicious to the untrained eye are, in fact, advantages to the trained one. Far from evidence of intent, Atlas's orbit is a reminder that nature's randomness can produce outcomes more dramatic than fiction. What excites our suspicion is, paradoxically, what empowers our science. To understand why Atlas's trajectory feels so uncanny, it helps to place it alongside the two other interstellar objects humanity has met. The first, Oumuamua, discovered in 2017, was a traveler like no other, fast, elongated, and oddly lacking a coma. It slipped through the solar system on a steep, oblique path, cutting across the planetary plane with little regard for alignment. Its trajectory was peculiar enough to raise eyebrows, but not because it hugged the ecliptic. Instead, the mystery was its acceleration, its shape, and its silence. Some wondered if radiation pressure was pushing it. Others flirted with the notion of technology. But the geometry itself did not suggest intent. It suggested speed and strangeness, not alignment. 2 years later came Borisov, a very different guest. Discovered in 2019, Borisov looked and behaved much like comets we already knew. It had a dusty tail, a composition dominated by water, and a trajectory angled enough that no one mistook it for purposeful. Its steep inclination placed it clearly outside the planetary lanes. Borisov reassured us that interstellar comets could be familiar, could echo the bodies that circle our own Sunday. In Borisov, we saw a reminder of continuity. In Oumuamua, we saw a challenge to definition. And now, in Atlas, we see something else entirely. Alignment so close it feels personal, combined with retrograde defiance that makes it look intentional, even when it is not. This difference explains much of the public fascination. Atlas does not just pass through, it lingers in familiar territory. It is as if an outsider walked not across our lawn but down the middle of our living room. The geometry alone feels invasive. And because the comet is retrograde, the sense of confrontation deepens. It moves against the grain, the cosmic equivalent of swimming upstream or walking against a crowd. When something foreign chooses the most visible, most disruptive path, we instinctively ascribe intention. But the word chooses is where the trap lies. Atlas does not choose, it travels. The intention is ours, loudest's. Psychologists call this the intentionality bias, the human tendency to attribute purpose to random movement. It is a survival instinct. If a shadow flickers in the forest, assuming it is a predator can save your life. If the wind rustles grass, imagining an animal teaches caution. Better to over-ascribe intention than to miss real danger. But that instinct, so valuable in evolution, misleads us in science. We see a comet aligned with the ecliptic and imagine steering. We see a plume pointing sunward and imagine defiance. We see patterns and assign stories. Atlas becomes not a rock and ice body from afar, but an actor in a play we are writing for it. This is why selection bias and intentionality bias feed one another. Out of infinite interstellar paths, we remember only the ones that look strange. Out of infinite behaviors, we remember only the ones that look deliberate. Atlas fits both categories, rare geometry and rare volatility, and so it absorbs all our projections. To some, it becomes a messenger. To others, a threat. To a few, even a candidate for technology. But in reality, it is none of those things. It is an object following the path gravity dictates, carved by chance long before it entered our sky. The only intention is the one we project upon it. Yet in dismantling the myth of intent, we do not diminish Atlas's wonder. Quite the opposite. The fact that random chance can produce such dramatic alignments is more astonishing than any theory of control. A deliberate visitor would be remarkable. A random one that happens to align so perfectly is awe in its purest form. It means the universe can generate moments that look like theatre without actors, choreography without choreographers. For scientists, this is not disappointment but exhilaration. It means there are still surprises in the equations, still poetry in the probabilities. Atlas is not intentional, but it is extraordinary, and extraordinary is enough. The final and most important point about Atlas's orbit is not how strange it looks, but how we choose to interpret that strangeness. The temptation to speak of intent is powerful because it satisfies our need for story. But science is not served by story, it is served by scrutiny. When astronomers map Atlas's trajectory, what they see is not evidence of purpose, but evidence of probability intersecting with opportunity. A retrograde orbit aligned so close to the ecliptic is rare, yes, but rarity is not the same as design. The solar system is vast, and the number of possible approach vectors is effectively infinite. Eventually, one of those vectors was bound to look meaningful to us. Atlas just happens to be the one. The challenge now is to resist reading significance into coincidence. That resistance is not boring, it is discipline. It is what separates careful science from the noise of speculation. And within that discipline lies the wonder of a different kind. Because Atlas skims the ecliptic, our instruments are perfectly positioned to study it. Earth-based telescopes can track it without awkward tilts. Spacecraft orbiting Mars and Earth can capture data along the same plane. Even the relative velocity created by its retrograde path becomes a gift. Particles and photons collide with detectors at higher energy, sharpening measurements that would otherwise be blurred. The very geometry that seems uncanny to the untrained eye becomes a scientific windfall to the trained one. If this were a scripted encounter, no stage manager could design a better setup for observation. Atlas does not need to be extraordinary. Its orbit alone gives us one of the best interstellar laboratories we have ever had. This is why caution is not a dampening of drama, but its amplification. The true story of Atlas's trajectory is not that it looks deliberate, but that its natural path produces extraordinary chances to learn. Conspiracy theories reduce Atlas to a pawn of imagined design. Science elevates Atlas to a cosmic messenger without intention, a wanderer whose random chance enriches our understanding. That reframing is not only intellectually satisfying, it is emotionally grounding. It replaces fear with focus, replacing "what does it want?" with "what can it teach?" The first question leads to paranoia, the second leads to discovery, and in that difference lies the value of restraint. Still, we must acknowledge the paradox. To the public, silence and caution often look like concealment. To the scientific community, they look like responsibility. Atlas's orbit illustrates why this gap matters. Left unexplained, the retrograde alignment feels ominous. Properly explained, it becomes an opportunity. That shift in framing is everything. It turns a highway crash into a highway experiment, a near miss into a near miracle of observation. And it proves why scientific voices must step forward, not to hype, but to clarify, not to dramatize, but to contextualize. Atlas does not need our embellishments. It is already extraordinary enough. As Atlas moves forward on its path, the focus must remain on evidence. The inclination, the perihelion, the Mars flyby, the December reappearance, each is a receipt that can be checked and verified. The speculation about intent cannot be verified, it cannot be tested, and science without testability is not science at all. That is why restraint matters. It does not deny wonder, it preserves it. It does not strip meaning, it protects meaning from distortion. In the end, Atlas is not a car entering the highway with malice. It is a pebble hurled by chance across cosmic lanes, arriving in our sightline in a way that looks uncanny only because our minds are tuned to see patterns. The pebble carries no will, but in studying it carefully, we may find knowledge that shapes our own, and that, in the end, is intent enough, not Atlas's, but ours. Some opportunities in science are so rare that they are measured not in years or decades but in centuries. Astronomers call them golden windows, brief alignments, when nature hands us a chance that will not return in a human lifetime. For 3, I divided by Atlas. That golden window opened between October 1st and October 7th, 2025. During that single week, the comet swept unusually close to Mars, close enough that orbiters already circling the red planet could turn their instruments toward it. For planetary scientists, this was the dream scenario. Earth-based telescopes could track Atlas, yes, but our atmosphere blurs and absorbs much of the signal. Mars, stripped of a dense sky and armed with spectrometers orbiting above, offered something Earth could not: a pristine vantage point, a cosmic laboratory floating in the right place at the right time. And the timing mattered. Miss it, and Atlas would streak past, never to return. The numbers themselves are stark. On October 3rd, Atlas reached its closest approach to Mars at roughly 0.19 astronomical units, about 30 million kilometers. To the uninitiated, that distance sounds immense, a gulf impossible to cross. But to astronomers, it was close, tantalizingly close. On cosmic scales, that kind of proximity is like leaning over a balcony as a parade passes beneath, not so close as to touch, but close enough to see detail you would otherwise miss. Every kilometer mattered, because every kilometer reduced uncertainty and increased precision. Atlas was not a dot on a faraway chart anymore. It was a target within reach of our best tools. And what tools they were! The European Space Agency's trace gas orbiter, ERA-GEO, originally designed to study the thin Martian atmosphere, suddenly became a cometary observatory by proxy. Its Nomad spectrometer, nadir and occultation for Mars discovery, is capable of passing sunlight filtered through gases at parts per billion levels. Alongside Nomad, the Atmospheric Chemistry Suite, ACS, brings multiple infrared channels, each tuned to different molecules. Between them, Nomad and ACS could trace carbon dioxide, methane, water vapor, and other volatiles with exquisite accuracy. Meanwhile, ESA's veteran Mars Express, orbiting since 2003, carried legacy but still formidable instruments. Its SpyCam spectrometer had measured the Martian sky for nearly 2 decades, while Omega mapped minerals and ices across the red planet's surface. In early October 2025, all of these instruments turned outward, away from Mars, toward the strange visitor streaking past. It was as if 2 entire missions, designed for one world, had been temporarily repurposed to interrogate another. The excitement was palpable in mission control. Teams in Darmstadt, Paris, and Madrid worked around the clock, recalculating trajectories, uploading new observation scripts, and coordinating pointing schedules. Atlas was moving at nearly 60 kilometers per second. Missing a window by hours meant losing data forever. Scientists spoke later of the tension, coffee-fueled nights, whispered calculations, and the sheer pressure of knowing that the comet would never give them a second chance. They were not dramatizing. For every planned observation, there was no redo. If an instrument failed to lock on, or if timing was even slightly off, the comet would slip away, and the record would be blank. The opportunity was fragile, fleeting, and irreplaceable. For the public, October 3rd came and went with little fanfare. But within the walls of ESA, it was a climax. At the moment of closest approach, TGO's spectrometers drank photons from a body that had formed under another star. Mars Express logged scattering curves from dust grains that might never have existed in our solar system. Later, when the raw spectra were processed, the results showed jagged peaks and valleys, signatures of carbon dioxide dominating the gas, irregular brightness fluctuations, hinting at outbursts, and subtle shifts in dust reflectance that scientists are still debating. Those graphs, meaningless to most eyes, were historic to the few who could read them. They were receipts of contact, evidence that humanity had, however briefly, extended its senses into interstellar chemistry. And this was only possible because of geometry. Atlas's alignment with the ecliptic meant Mars happened to sit in the right position to intercept its signal. No one could plan such fortune. It was handed to us by chance. But once fortune opened the door, preparation walked through it. The golden window was not wasted. The orbiters turned, the detectors opened, and for one short week, our species reached beyond its solar cradle to touch a messenger from elsewhere. It was science at its most exhilarating, fragile, fleeting, and unforgettable. To understand why the Mars campaign mattered, you have to step inside the instruments themselves. Each one is not just a box of metal and optics, it is a translator, a machine designed to turn starlight into language we can read. During the golden week of October 2025, these translators were tuned away from Mars and toward 3I, divided by Atlas, and the orchestra they formed was astonishing in its precision. Start with Nomad, the jewel of the trace gas orbiter. Its name, Nadir, an occultation for Mars discovery, sounds specialized, but its essence is simple. It catches sunlight that has passed through a gas, splits it into wavelengths, and measures which ones are missing. Each missing line corresponds to a molecule that absorbed it, like a fingerprint on a piece of glass. With sensitivity down to parts per billion, Nomad can identify gases so faint they would vanish into noise for less powerful spectrometers. For Mars, that meant methane searches. For Atlas, it meant dissecting the balance of volatiles in its coma. On October 3rd, Nomad looked at the interstellar visitor and found carbon dioxide shouting louder than water, an inversion of everything solar system comets had taught us. That fingerprint alone was worth the campaign. Besides it, ACS, the atmospheric chemistry suite, extended Nomad's reach. Where Nomad specializes in the ultraviolet and visible range, ACS commands the infrared, splitting light into longer wavelengths where molecules like CO2, CH4, and H2O leave deeper scars. ACS carries 3 spectrometers, each designed for a different spectral window, overlapping to cover a broad swath of the chemical palette. On Earth, we know infrared as heat. In space, it is the key to decoding the breath of comets. When ACS pointed at Atlas, its sensors captured jagged lines of absorption that spoke of volatile outbursts, erratic and irregular. The data showed that Atlas did not exhale evenly. It pulsed, vented, and flickered, as if its nucleus were riddled with hidden pockets, releasing gas in chaotic bursts. Where Nomad confirmed the CO2 dominance, ACS added texture, not just what molecules were there, but how unstable their release could be. Meanwhile, Mars Express, ESA's veteran spacecraft, carried its own instruments into the hunt. SpyCam spectroscopy, for investigation of characteristics of the atmosphere of Mars, was designed to study ultraviolet and infrared absorption in Mars's thin sky. But during the campaign, SpyCam looked outward, catching faint ultraviolet signals from Atlas. Ultraviolet is unforgiving. It reveals atomic emissions, ionization, and the play of solar wind on escaping gases. Through SpyCam's eyes, Atlas looked jagged, its coma sliced by interactions we had never seen in such an interstellar body. Each photon was a whisper of chemistry under stress, and SpyCam recorded them with stoic patience. And then there was Omega, the mineralogist's tool. Omega's specialty is mapping the Martian surface in visible and near-infrared bands, identifying ices and minerals by their spectral signatures. But in October 2025, Omega became a comet watcher. By measuring the sunlight reflected off Atlas's dust grains, it hinted at their composition, grain size, and scattering properties. Were the grains fine and fluffy, like smoke, or coarse and heavy, like sand? Omega's data leaned toward the latter, consistent with the puzzling sunward plume seen in telescopes, larger particles that resisted the solar wind, drifting in unexpected directions. For the first time, we had evidence that Atlas's dust behaved differently from the familiar comets of our own system. Together, Nomad, ACS, SpyCam, and Omega formed a symphony of observation. Each played a different note, and together they produced harmony. A comet with alien chemistry, erratic outgassing, strange dust dynamics, and ultraviolet emissions shaped by the solar wind. The story they told was richer than any one instrument could have produced, and yet, behind the excitement, there was tension. Every orbit of TGO or Mars Express offered only narrow observation windows. Teams had to calculate pointing times with ruthless accuracy, often to the second. A missed command sequence meant a lost dataset. Scientists spoke of the anxiety of staring at consoles while raw photon counts trickled in, hoping the lines would resolve into usable spectra. For them, the thrill of discovery was inseparable from the fear of failure. When the week ended, relief mixed with exhaustion. The campaign had succeeded, the instruments had delivered. The receipts of Atlas's alien nature were secured in files and servers across Europe, and yet, no one doubted the fragility of it all. If weather had interfered, if timing had slipped, if a glitch had struck, the record would be blank. That is why this golden week mattered so deeply. It was not just data collection, it was proof of readiness. Humanity had been given a fleeting target, and through coordination and discipline, we had not missed. When the golden week ended on October 7th, relief swept through every control room involved. For 7 days, orbiters had bent their schedules, scientists had lost sleep, and instruments had stretched beyond their original missions. Now the data was secured, tucked away in servers from Madrid to Paris, awaiting careful calibration. The tension dissolved into something more enduring: excitement. Because even in their rawest forms, the spectra and light curves carried unmistakable signatures. Atlas had not disappointed. It had delivered anomalies that confirmed suspicions, challenged models, and hinted at deeper mysteries still waiting to be unraveled. The first analysis confirmed what ground-based telescopes had already whispered: carbon dioxide dominated. Nomad's measurements pinned the CO2 to H2O ratio firmly in the range of 8:1, an alien chemistry that demanded explanation. But the Mars campaign added nuance. ACS detected irregular outbursts, bursts of volatile release that suggested pressure pockets or layered ices hidden beneath the nucleus's surface. SpyCam recorded ultraviolet emissions consistent with solar wind interactions, showing that Atlas's coma was not passive but reactive, a stage where particles collided, ionized, and danced. Omega traced dust grains larger than expected, their scattering behavior aligning with the puzzling sunward plume. Taken together, the data painted a picture of a comet unlike any we had catalogued before: chemically inverted, behaviorally restless, and structurally peculiar. Scientists knew immediately that it would take months, even years, to wring every insight from the files. But even in October, the outlines of the story were clear. Atlas was no ordinary interstellar visitor. Its composition suggested a birthplace far from the warm, water-rich nurseries that produced comets in our solar system. Its volatility hinted at an internal architecture layered and fragile. Its dust betrayed dynamics that bent familiar rules. This was not just another data point. It was a challenge, a demand to expand our models of planetary system formation, to widen our imagination of what normal can mean in a galaxy filled with worlds we cannot yet see. For those inside the campaign, the emotional impact was as real as the scientific one. They spoke of the surreal experience of watching raw counts rise on a screen, knowing those photons had traveled not from Mars or Earth, but from an object born around another star. They compared it to hearing a voice carried across an ocean, faint but undeniable, the voice of somewhere else. The campaign had given humanity not just data but connection, a tangible link to the broader galaxy, recorded in spectra and counts, and jagged lines on a monitor. It was proof that the universe is not abstract, it is present, touchable, measurable, if only for a fleeting moment. And yet, with the excitement came a sobering reminder. The window had closed. Atlas was moving on, racing toward perihelion at the end of October, where the sun's glare would swallow it from Earth's perspective. No instrument on Mars or Earth could follow it through that blinding stretch. For weeks, Atlas would vanish, hidden in brilliance, leaving only models and anticipation. Would it survive? Would its chemistry shift as deeper layers are exposed? Would it fragment into dust, leaving only memory behind? No one knew. The Golden Week had given us answers, but it had also sharpened the questions. The comet was not finished speaking, it was only pausing, waiting for December to return to our skies. That paradox of triumph and tension, of discovery and delay, is what makes the Mars campaign unforgettable. For 7 days, humanity reached across millions of kilometers to sample an interstellar relic we did not miss. We collected receipts of alien chemistry, erratic behavior, and strange dust. But the story is unfinished. The blackout of perihelion looms, a silence in which we can only wait. What Atlas has already told us is extraordinary. What it may yet reveal is unknown. And as the golden window closed, the scientific community braced itself for the next phase of the drama. The long pause of blinding sunlight, followed by the suspense of reappearance. The campaign had given us the taste of connection. Now, the cosmos demanded patience. This instinct to project meaning onto geometry is deeply human. We evolved to detect patterns, faces in clouds, constellations in stars, purpose in coincidence. A comet threading the planetary plane invites the same projection. The orbit looks neat, precise, deliberate. But probability ensures that out of countless random interstellar approaches, some will appear this way. The key word is appear. Atlas's trajectory is not evidence of control. It is evidence of chance creating shapes that our minds are primed to interpret as purpose. This is the essence of selection bias. We remember the rare alignments that look extraordinary and forget the countless trajectories that looked unremarkable. Atlas is memorable precisely because it excites our bias, not because it carries intention. To see this more clearly, imagine flipping a coin 1,000 times. By chance, you will sometimes get 10 heads in a row. When that streak appears, it feels uncanny, even magical, but mathematics insists it must happen eventually. Atlas's orbit is our streak of heads. It looks special because it is unusual, but unusual does not mean intentional. It means that, in a vast universe with billions of random vectors, one of them was bound to align in a way that would catch our attention. We notice Atlas not because it proves design, but because our attention is wired to notice it. The irony is that in resisting speculation, scientists find greater wonder than any conspiracy could offer. To them, Atlas's low inclination is not a hint of alien steering but an observational gift. Its alignment makes it easier to track with instruments already pointed along the ecliptic. Its retrograde velocity increases the relative speeds of particles and photons, sharpening spectroscopic measurements. The very features that look suspicious to the untrained eye are, in fact, advantages to the trained one. Far from evidence of intent, Atlas's orbit is a reminder that nature's randomness can produce outcomes more dramatic than fiction. What excites our suspicion is, paradoxically, what empowers our science. To understand why Atlas's trajectory feels so uncanny, it helps to place it alongside the 2 other interstellar objects humanity has met. The first, Oumuamua, discovered in 2017, was a traveler like no other, fast, elongated, and oddly lacking a coma. It slipped through the solar system on a steep, oblique path, cutting across the planetary plane with little regard for alignment. Its trajectory was peculiar enough to raise eyebrows, but not because it hugged the ecliptic. Instead, the mystery was its acceleration, its shape, and its silence. Some wondered if radiation pressure was pushing it. Others flirted with the notion of technology. But the geometry itself did not suggest intent. It suggested speed and strangeness, not alignment. 2 years later came Borisov, a very different guest. Discovered in 2019, Borisov looked and behaved much like comets we already knew. It had a dusty tail, a composition dominated by water, and a trajectory angled enough that no one mistook it for purposeful. Its steep inclination placed it clearly outside the planetary lanes. Borisov reassured us that interstellar comets could be familiar, could echo the bodies that circle our own Sunday. In Borisov, we saw a reminder of continuity. In Oumuamua, we saw a challenge to definition. And now, in Atlas, we see something else entirely. Alignment so close it feels personal, combined with retrograde defiance that makes it look intentional, even when it is not. This difference explains much of the public fascination. Atlas does not just pass through, it lingers in familiar territory. It is as if an outsider walked not across our lawn but down the middle of our living room. The geometry alone feels invasive. And because the comet is retrograde, the sense of confrontation deepens. It moves against the grain, the cosmic equivalent of swimming upstream or walking against a crowd. When something foreign chooses the most visible, most disruptive path, we instinctively ascribe intention. But the word chooses is where the trap lies. Atlas does not choose, it travels. The intention is ours, loudest's. Psychologists call this the intentionality bias, the human tendency to attribute purpose to random movement. It is a survival instinct. If a shadow flickers in the forest, assuming it is a predator can save your life. If the wind rustles grass, imagining an animal teaches caution. Better to over-ascribe intention than to miss real danger. But that instinct, so valuable in evolution, misleads us in science. We see a comet aligned with the ecliptic and imagine steering. We see a plume pointing sunward and imagine defiance. We see patterns and assign stories. Atlas becomes not a rock and ice body from afar, but an actor in a play we are writing for it. This is why selection bias and intentionality bias feed one another. Out of infinite interstellar paths, we remember only the ones that look strange. Out of infinite behaviors, we remember only the ones that look deliberate. Atlas fits both categories, rare geometry and rare volatility, and so it absorbs all our projections. To some, it becomes a messenger. To others, a threat. To a few, even a candidate for technology. But in reality, it is none of those things. It is an object following the path gravity dictates, carved by chance long before it entered our sky. The only intention is the one we project upon it. Yet in dismantling the myth of intent, we do not diminish Atlas's wonder. Quite the opposite. The fact that random chance can produce such dramatic alignments is more astonishing than any theory of control. A deliberate visitor would be remarkable. A random one that happens to align so perfectly is awe in its purest form. It means the universe can generate moments that look like theatre without actors, choreography without choreographers. For scientists, this is not disappointment but exhilaration. It means there are still surprises in the equations, still poetry in the probabilities. Atlas is not intentional, but it is extraordinary, and extraordinary is enough. The final and most important point about Atlas's orbit is not how strange it looks, but how we choose to interpret that strangeness. The temptation to speak of intent is powerful because it satisfies our need for story. But science is not served by story. It is served by scrutiny. When astronomers map Atlas's trajectory, what they see is not evidence of purpose, but evidence of probability intersecting with opportunity. A retrograde orbit aligned so close to the ecliptic is rare, yes, but rarity is not the same as design. The solar system is vast, and the number of possible approach vectors is effectively infinite. Eventually, one of those vectors was bound to look meaningful to us. Atlas just happens to be the one. The challenge now is to resist reading significance into coincidence. That resistance is not boring, it is discipline. It is what separates careful science from the noise of speculation. And within that discipline lies the wonder of a different kind. Because Atlas skims the ecliptic, our instruments are perfectly positioned to study it. Earth-based telescopes can track it without awkward tilts. Spacecraft orbiting Mars and Earth can capture data along the same plane. Even the relative velocity created by its retrograde path becomes a gift. Particles and photons collide with detectors at higher energy, sharpening measurements that would otherwise be blurred. The very geometry that seems uncanny to the untrained eye becomes a scientific windfall to the trained one. If this were a scripted encounter, no stage manager could design a better setup for observation. Atlas does not need to be extraordinary. Its orbit alone gives us one of the best interstellar laboratories we have ever had. This is why caution is not a dampening of drama, but its amplification. The true story of Atlas's trajectory is not that it looks deliberate, but that its natural path produces extraordinary chances to learn. Conspiracy theories reduce Atlas to a pawn of imagined design. Science elevates Atlas to a cosmic messenger without intention, a wanderer whose random chance enriches our understanding. That reframing is not only intellectually satisfying, it is emotionally grounding. It replaces fear with focus, replacing "what does it want?" with "what can it teach?" The first question leads to paranoia, the second leads to discovery, and in that difference lies the value of restraint. Still, we must acknowledge the paradox. To the public, silence and caution often look like concealment. To the scientific community, they look like responsibility. Atlas's orbit illustrates why this gap matters. Left unexplained, the retrograde alignment feels ominous. Properly explained, it becomes an opportunity. That shift in framing is everything. It turns a highway crash into a highway experiment, a near miss into a near miracle of observation. And it proves why scientific voices must step forward, not to hype, but to clarify, not to dramatize, but to contextualize. Atlas does not need our embellishments. It is already extraordinary enough. As Atlas moves forward on its path, the focus must remain on evidence. The inclination, the perihelion, the Mars flyby, the December reappearance, each is a receipt that can be checked and verified. The speculation about intent cannot be verified, it cannot be tested, and science without testability is not science at all. That is why restraint matters. It does not deny wonder, it preserves it. It does not strip meaning, it protects meaning from distortion. In the end, Atlas is not a car entering the highway with malice. It is a pebble hurled by chance across cosmic lanes, arriving in our sightline in a way that looks uncanny only because our minds are tuned to see patterns. The pebble carries no will, but in studying it carefully, we may find knowledge that shapes our own, and that, in the end, is intent enough, not Atlas's, but ours. Some opportunities in science are so rare that they are measured not in years or decades, but in centuries. Astronomers call them golden windows, brief alignments, when nature hands us a chance that will not return in a human lifetime. For 3, I divided by Atlas. That golden window opened between October 1st and October 7th, 2025. During that single week, the comet swept unusually close to Mars, close enough that orbiters already circling the red planet could turn their instruments toward it. For planetary scientists, this was the dream scenario. Earth-based telescopes could track Atlas, yes, but our atmosphere blurs and absorbs much of the signal. Mars, stripped of a dense sky and armed with spectrometers orbiting above, offered something Earth could not: a pristine vantage point, a cosmic laboratory floating in the right place at the right time. And the timing mattered. Miss it, and Atlas would streak past, never to return. The numbers themselves are stark. On October 3rd, Atlas reached its closest approach to Mars at roughly 0.19 astronomical units, about 30 million kilometers. To the uninitiated, that distance sounds immense, a gulf impossible to cross. But to astronomers, it was close, tantalizingly close. On cosmic scales, that kind of proximity is like leaning over a balcony as a parade passes beneath, not so close as to touch, but close enough to see detail you would otherwise miss. Every kilometer mattered, because every kilometer reduced uncertainty and increased precision. Atlas was not a dot on a faraway chart anymore. It was a target within reach of our best tools. And what tools they were! The European Space Agency's Trace Gas Orbiter, ERA-GEO, originally designed to study the thin Martian atmosphere, suddenly became a cometary observatory by proxy. Its Nomad spectrometer, nadir and occultation for Mars discovery, is capable of passing sunlight filtered through gases at parts per billion levels. Alongside Nomad, the Atmospheric Chemistry Suite, ACS, brings multiple infrared channels, each tuned to different molecules. Between them, Nomad and ACS could trace carbon dioxide, methane, water vapor, and other volatiles with exquisite accuracy. Meanwhile, ESA's veteran Mars Express, orbiting since 2003, carried legacy but still formidable instruments. Its SpyCam spectrometer had measured the Martian sky for nearly 2 decades, while Omega mapped minerals and ices across the red planet's surface. In early October 2025, all of these instruments turned outward, away from Mars, toward the strange visitor streaking past. It was as if 2 entire missions, designed for one world, had been temporarily repurposed to interrogate another. The excitement was palpable in mission control. Teams in Darmstadt, Paris, and Madrid worked around the clock, recalculating trajectories, uploading new observation scripts, and coordinating pointing schedules. Atlas was moving at nearly 60 kilometers per second. Missing a window by hours meant losing data forever. Scientists spoke later of the tension, coffee-fueled nights, whispered calculations, and the sheer pressure of knowing that the comet would never give them a second chance. They were not dramatizing. For every planned observation, there was no redo. If an instrument failed to lock on, or if timing was even slightly off, the comet would slip away, and the record would be blank. The opportunity was fragile, fleeting, and irreplaceable. For the public, October 3rd came and went with little fanfare. But within the walls of ESA, it was a climax. At the moment of closest approach, TGO's spectrometers drank photons from a body that had formed under another star. Mars Express logged scattering curves from dust grains that might never have existed in our solar system. Later, when the raw spectra were processed, the results showed jagged peaks and valleys, signatures of carbon dioxide dominating the gas, irregular brightness fluctuations, hinting at outbursts, and subtle shifts in dust reflectance that scientists are still debating. Those graphs, meaningless to most eyes, were historic to the few who could read them. They were receipts of contact, evidence that humanity had, however briefly, extended its senses into interstellar chemistry. And this was only possible because of geometry. Atlas's alignment with the ecliptic meant Mars happened to sit in the right position to intercept its signal. No one could plan such fortune. It was handed to us by chance. But once fortune opened the door, preparation walked through it. The golden window was not wasted. The orbiters turned, the detectors opened, and for one short week, our species reached beyond its solar cradle to touch a messenger from elsewhere. It was science at its most exhilarating, fragile, fleeting, and unforgettable. To understand why the Mars campaign mattered, you have to step inside the instruments themselves. Each one is not just a box of metal and optics, it is a translator, a machine designed to turn starlight into language we can read. During the golden week of October 2025, these translators were tuned away from Mars and toward 3I, divided by Atlas, and the orchestra they formed was astonishing in its precision. Start with Nomad, the jewel of the trace gas orbiter. Its name, Nadir, an occultation for Mars discovery, sounds specialized, but its essence is simple. It catches sunlight that has passed through a gas, splits it into wavelengths, and measures which ones are missing. Each missing line corresponds to a molecule that absorbed it, like a fingerprint on a piece of glass. With sensitivity down to parts per billion, Nomad can identify gases so faint they would vanish into noise for less powerful spectrometers. For Mars, that meant methane searches. For Atlas, it meant dissecting the balance of volatiles in its coma. On October 3rd, Nomad looked at the interstellar visitor and found carbon dioxide shouting louder than water, an inversion of everything solar system comets had taught us. That fingerprint alone was worth the campaign. Besides it, ACS, the atmospheric chemistry suite, extended Nomad's reach. Where Nomad specializes in the ultraviolet and visible range, ACS commands the infrared, splitting light into longer wavelengths where molecules like CO2, CH4, and H2O leave deeper scars. ACS carries 3 spectrometers, each designed for a different spectral window, overlapping to cover a broad swath of the chemical palette. On Earth, we know infrared as heat. In space, it is the key to decoding the breath of comets. When ACS pointed at Atlas, its sensors captured jagged lines of absorption that spoke of volatile outbursts, erratic and irregular. The data showed that Atlas did not exhale evenly. It pulsed, vented, and flickered, as if its nucleus were riddled with hidden pockets, releasing gas in chaotic bursts. Where Nomad confirmed the CO2 dominance, ACS added texture, not just what molecules were there, but how unstable their release could be. Meanwhile, Mars Express ESA's veteran spacecraft, carried its own instruments into the hunt. SpyCam spectroscopy, for investigation of characteristics of the atmosphere of Mars, was designed to study ultraviolet and infrared absorption in Mars's thin sky. But during the campaign, SpyCam looked outward, catching faint ultraviolet signals from Atlas. Ultraviolet is unforgiving. It reveals atomic emissions, ionization, and the play of solar wind on escaping gases. Through SpyCam's eyes, Atlas looked jagged, its coma sliced by interactions we had never seen in such an interstellar body. Each photon was a whisper of chemistry under stress, and SpyCam recorded them with stoic patience. And then there was Omega, the mineralogist's tool. Omega's specialty is mapping the Martian surface in visible and near-infrared bands, identifying ices and minerals by their spectral signatures. But in October 2025, Omega became a comet watcher. By measuring the sunlight reflected off Atlas's dust grains, it hinted at their composition, grain size, and scattering properties. Were the grains fine and fluffy, like smoke, or coarse and heavy, like sand? Omega's data leaned toward the latter, consistent with the puzzling sunward plume seen in telescopes, larger particles that resisted the solar wind, drifting in unexpected directions. For the first time, we had evidence that Atlas's dust behaved differently from the familiar comets of our own system. Together, Nomad, ACS, SpyCam, and Omega formed a symphony of observation. Each played a different note, and together they produced harmony. A comet with alien chemistry, erratic outgassing, strange dust dynamics, and ultraviolet emissions shaped by the solar wind. The story they told was richer than any one instrument could have produced, and yet, behind the excitement, there was tension. Every orbit of TGO or Mars Express offered only narrow observation windows. Teams had to calculate pointing times with ruthless accuracy, often to the second. A missed command sequence meant a lost dataset. Scientists spoke of the anxiety of staring at consoles while raw photon counts trickled in, hoping the lines would resolve into usable spectra. For them, the thrill of discovery was inseparable from the fear of failure. When the week ended, relief mixed with exhaustion. The campaign had succeeded, the instruments had delivered. The receipts of Atlas's alien nature were secured in files and servers across Europe, and yet, no one doubted the fragility of it all. If weather had interfered, if timing had slipped, if a glitch had struck, the record would be blank. That is why this golden week mattered so deeply. It was not just data collection, it was proof of readiness. Humanity had been given a fleeting target, and through coordination and discipline, we had not missed. When the golden week ended on October 7th, relief swept through every control room involved. For 7 days, orbiters had bent their schedules, scientists had lost sleep, and instruments had stretched beyond their original missions. Now the data was secured, tucked away in servers from Madrid to Paris, awaiting careful calibration. The tension dissolved into something more enduring: excitement. Because even in their rawest forms, the spectra and light curves carried unmistakable signatures. Atlas had not disappointed. It had delivered anomalies that confirmed suspicions, challenged models, and hinted at deeper mysteries still waiting to be unraveled. The first analysis confirmed what ground-based telescopes had already whispered. Carbon dioxide dominated. Nomad's measurements pinned the CO2 to H2O ratio firmly in the range of 8:1, an alien chemistry that demanded explanation. But the Mars campaign added nuance. ACS detected irregular outbursts, bursts of volatile release that suggested pressure pockets or layered ices hidden beneath the nucleus's surface. SpyCam recorded ultraviolet emissions consistent with solar wind interactions, showing that Atlas's coma was not passive but reactive, a stage where particles collided, ionized, and danced. Omega traced dust grains larger than expected, their scattering behavior aligning with the puzzling sunward plume. Taken together, the data painted a picture of a comet unlike any we had catalogued before: chemically inverted, behaviorally restless, and structurally peculiar. Scientists knew immediately that it would take months, even years, to wring every insight from the files. But even in October, the outlines of the story were clear. Atlas was no ordinary interstellar visitor. Its composition suggested a birthplace far from the warm, water-rich nurseries that produced comets in our solar system. Its volatility hinted at an internal architecture layered and fragile. Its dust betrayed dynamics that bent familiar rules. This was not just another data point. It was a challenge, a demand to expand our models of planetary system formation, to widen our imagination of what normal can mean in a galaxy filled with worlds we cannot yet see. For those inside the campaign, the emotional impact was as real as the scientific one. They spoke of the surreal experience of watching raw counts rise on a screen, knowing those photons had traveled not from Mars or Earth, but from an object born around another star. They compared it to hearing a voice carried across an ocean, faint but undeniable, the voice of somewhere else. The campaign had given humanity not just data but connection, a tangible link to the broader galaxy, recorded in spectra and counts, and jagged lines on a monitor. It was proof that the universe is not abstract, it is present, touchable, measurable, if only for a fleeting moment. And yet, with the excitement came a sobering reminder. The window had closed. Atlas was moving on, racing toward perihelion at the end of October, where the sun's glare would swallow it from Earth's perspective. No instrument on Mars or Earth could follow it through that blinding stretch. For weeks, Atlas would vanish, hidden in brilliance, leaving only models and anticipation. Would it survive? Would its chemistry shift as deeper layers are exposed? Would it fragment into dust, leaving only memory behind? No one knew. The Golden Week had given us answers, but it had also sharpened the questions. The comet was not finished speaking, it was only pausing, waiting for December to return to our skies. That paradox of triumph and tension, of discovery and delay, is what makes the Mars campaign unforgettable. For 7 days, humanity reached across millions of kilometers to sample an interstellar relic we did not miss. We collected receipts of alien chemistry, erratic behavior, and strange dust. But the story is unfinished. The blackout of perihelion looms, a silence in which we can only wait. What Atlas has already told us is extraordinary. What it may yet reveal is unknown. And as the golden window closed, the scientific community braced itself for the next phase of the drama. The long pause of blinding sunlight, followed by the suspense of reappearance. The campaign had given us the taste of connection. Now, the cosmos demanded patience. Imagine a curtain of blinding sunlight swallowing a comet whole. One day, 3 divided by Atlas blazed across the sky with its strange chemistry and erratic light curve. The next, it slipped behind the solar glare, erased from every telescope on Earth. October 30th, 2025, was the day the curtain fell. The comet reached perihelion, the closest point to the Sun in its orbit. At that moment, Atlas passed just 1.4 astronomical units from our star, a distance that sounds vast but, in cosmic terms, placed it in a furnace of radiation and heat. For observers, however, the geometry was unforgiving. From Earth's perspective, the comet disappeared directly behind the Sun, lost in a wash of light that no optical or infrared instrument could penetrate. The blackout began, and with it came the most agonizing phase of this story, waiting. To understand why perihelion matters, think of it as the trial by fire for comets. Heat drives sublimation, sublimation drives activity, and activity can either strengthen or destroy. Some comets survive perihelion intact, their crusts sealed and hardened by centuries of interstellar cold. Others fracture catastrophically, bursting into fragments that dissolve into the solar wind. Still others transform, revealing hidden layers of chemistry as the deeper ices are exposed. Perihelion is not just a waypoint, it is the crucible where identities are forged or erased. And for Atlas, with its alien chemistry and erratic behavior, the stakes were higher than ever. What would emerge after the blackout? A survivor, a ghost, or something entirely unexpected? For scientists, the frustration was that the most critical act of the drama was invisible. Hubble, JWST, Subaru, VLT, every great telescope had to turn its gaze elsewhere, unable to risk the sun's blinding disk. Even spacecraft with solar shields could not watch. Their instruments are not designed to stare into brilliance. Geometry, not secrecy, forced the silence. But that knowledge did not make it easier to endure. Researchers described the last images of Atlas before it slipped away, streaking across sensors with unstable brightness, as if the comet were leaving a cliffhanger. Then came nothing. No spectra, no curves, no signal. For weeks stretching into December, the universe had turned off the lights on its most tantalizing visitor. This blindness magnified the uncertainty. Every hypothesis now hung suspended in the blackout. Would the CO2 dominance hold? Would water vapor suddenly surge? hinting at deeper layers? Would the erratic light curve collapse into dust as the nucleus disintegrated? Teams around the world ran simulations, debating probabilities, comparing Atlas to Borisov and to long-period comets of our solar system. Each model ended with a different outcome, and none could be confirmed. In the absence of data, imagination filled the void. Some predicted Atlas would not survive. Others placed their bets on a transformation, expecting new spectral ratios in December. All agreed on one point. No one could know until the curtain lifted. That suspense became the defining mood of late 2025. A mix of thrill and dread, scientific rigor and human restlessness. And yet, under the tension, there was hope. Hope that Atlas would survive the solar furnace and reveal new secrets when it returned to visibility in December. Hope that the golden week of Mars data had prepared scientists to read whatever came next. Hope that this interstellar visitor, even if transformed, would still carry messages from another star system. October 30th was the end of visibility, but it was not the end of the story. It was the intermission. The stage was dark, the actor unseen, but the performance was not over. Everyone, scientists, amateurs, and curious observers alike, waited for December, when the lights would rise again and Atlas would either reappear or vanish forever. When Atlas slipped behind the sun, science turned to a familiar tool: scenario planning. If you cannot watch the play unfold, you write possible endings in advance and wait to see which one matches reality. For Atlas, 3 scenarios dominated the discussion: survival, fragmentation, and transformation. Each carried its own probability, its own fingerprints, and its own implications for how interstellar bodies endure the crucible of perihelion. Scenario 1. Survival. In this version, Atlas emerges from blackout much as it entered, bruised by solar heat, but fundamentally intact. Its nucleus, perhaps larger and more cohesive than assumed, withstands the thermal stress. If this occurs, the December reappearance will show Atlas as a consistent point of light, following the predicted orbit, with brightness levels matching pre-perihelion models. The spectra will still be dominated by carbon dioxide, with water vapor perhaps appearing but not overwhelming. For planetary scientists, survival would be the most valuable outcome, because it allows extended observation across months. It would mean that Atlas is not merely a fleeting event but a sustained laboratory, offering time to refine models and confirm trends. For the public, survival would feel like triumph. The visitor has endured the sun's fire, carrying its alien chemistry onward. Scenario 2. Fragmentation. Many comets, including well-known ones like Ison in 2013, failed at perihelion, shattering under the stress of solar heating. If Atlas follows that path, its reappearance in December will be diffuse, not a single point but a fading cloud. The light curve will drop sharply, the spectra will flatten, and the images will show debris fanning out into space. Fragmentation would confirm suspicions that Atlas's erratic outbursts reflected structural weakness, pockets of gas and fragile layering that could not survive. To some, this would be a disappointment, cutting short the observational window. Yet even disintegration has value. By analyzing the dust cloud, scientists can infer composition, particle sizes, and release mechanisms in ways a stable nucleus conceals. In a sense, fragmentation is Atlas's final confession, scattering its secrets across space in a burst of light and dust. Scenario 3. Transformation. This is the most intriguing, the wild card. In this scenario, Atlas survives but changes. Its surface layers, rich in carbon dioxide, are exhausted at perihelion, exposing deeper layers where water ice dominates. When it reappears, the CO2 divided by H2O ratio shifts, perhaps dramatically. Its tail morphology changes, its spectrum evolves. Transformation would mean Atlas has multiple chemical strata, each revealed in sequence. For planetary science, this would be revolutionary. It would prove that interstellar comets are not homogeneous relics, but layered archives, storing records of different epochs in their birth systems. Detecting such a shift would require careful comparison of October and December data, exactly the kind of continuity that the Mars campaign and Earth-based telescopes were designed to provide. If transformation occurs, it will feel like a revelation, Atlas shedding one mask to reveal another. How will we know which scenario is real? The signatures are clear. If Atlas survives, its brightness will follow predictable models, its nucleus sharp. If it fragments, Observers will see diffuse smears and fading curves. If it transforms, the light will remain, but the chemistry will not. The spectral fingerprints will change. Carbon dioxide, giving way to water or other volatiles. Each possibility can be confirmed within days of its return to visibility. The suspense lies not in whether we will know, but in which receipt the universe will hand us. And so, in the silence of November 2025, astronomers kept their eyes on December, rehearsing each outcome in their minds. Survival promised stability, fragmentation promised revelation, transformation promised discovery. All three carried hope, even if in different forms. The blackout was not just an absence, it was anticipation, a cliffhanger written in light. And when the curtain rises, the cosmos will show which script it chose. November 2025 was a month of silence. Atlas was gone from every telescope, hidden in the blaze of the Sunday. Each evening, astronomers logged onto their systems, not to collect new data, but to confirm there was none. The feeds were blank. The sky offered no receipts. It was a strange kind of science, a month defined not by what could be measured, but by what could not. And in that void, tension grew. Scientists ran simulations again and again, projecting survival curves, modeling fragmentation scenarios, and testing transformation ratios. But every model ended the same way, awaiting confirmation. The universe had muted the instruments, and humanity could do nothing but speculate. Inside research institutes, the mood was restless. Teams that had worked day and night through the Mars campaign now found themselves pacing, waiting, analyzing the same October files from new angles. They spoke of rehearsing outcomes, like actors practicing 3 different endings without knowing which one the director would choose. Journals filled with preprints, hedged with careful words. If Atlas survives, we expect. Should Atlas fragment, we predict. Even the language bent under uncertainty. Nothing could be said without the conditional. The blackout was not just optical. It was linguistic, epistemic, and emotional. It was a pause imposed on knowledge itself. Outside the labs, the silence created a different effect. The media, hungry for a story, filled the vacuum with speculation. Headlines asked, has Atlas already disintegrated? Is the alien comet still alive? Talk shows debated their fate as though guessing a reality show outcome. Social media turned every rumor into trending content. A blurry image of a solar flare was miscaptioned as Atlas exploding. A faint streak in an unrelated telescope frame was labeled Atlas survives. In the absence of data, imagination became currency. Some saw menace, others miracle. But very few admitted the truth. No one knew. The blackout was a breeding ground for noise. This was where the voice of science mattered most. Astronomers stepped forward in interviews and podcasts, repeating the same sober mantra, we cannot know until December. They explained perihelion geometry, the impossibility of observations near the sun, and the difference between modeling and measurement. It was not a glamorous message. It did not satisfy the craving for instant answers. But it was essential. Without it, speculation would drown out reality entirely. One astrophysicist described it well. The hardest thing to communicate is the value of waiting, but waiting is sometimes the only honest position. That honesty, frustrating as it felt, kept the public tethered to fact in a season of rumor. For amateurs and enthusiasts, the silence was oddly thrilling. Forums buzzed with countdowns. 25 days until reappearance, 14 days to go. Backyard astronomers, unable to see Atlas, prepared their instruments anyway, running calibration tests, cleaning optics, rehearsing, tracking software. They were waiting for the curtain to rise, determined to be ready when it did. In that sense, November became less about absence and more about anticipation. The blackout was the tension before the reveal, the quiet before the music swells. And in that tension, hope survived. Hope that Atlas would come back bright. Hope that the data in December would settle arguments. Hope that the cosmos was saving its most dramatic act for the final scene. By the last week of November, the anticipation had become almost unbearable. The 3 scenarios, survival, fragmentation, transformation, had been repeated so often they felt like mythic archetypes. Survival was the hero's return, fragmentation, the tragic sacrifice, and transformation, the rebirth. Each possibility carried a story, each story carried an audience, and everyone, from seasoned spectroscopists to curious onlookers, was waiting for December to tell them which script the cosmos had chosen. December 2025 arrived, like the rising of a theatre curtain. For a month, the audience had sat in darkness, whispering guesses about how the play would end. Now the lights were about to return, and everyone, astronomers, amateurs, journalists, and curious night sky watchers, leaned forward in their seats. Would Atlas step back onto the stage, bright and intact? Would it appear as a cloud of fading dust, a ghost of what it once was? Or would it surprise us with new chemistry, shedding one mask and revealing another? The suspense was not metaphorical, it was scientific. Because the signatures were clear, and within days of reappearance, the cosmos would tell us which script it had chosen. The first clue would come from brightness. Survival would mean Atlas shone at or near its predicted magnitude, a steady point returning to its track. Fragmentation would mean dimness, a blurred glow dispersing into nothing. Transformation would be subtler, the comet still visible, but its light behaving oddly, brightening or fading in ways that hinted at internal change. Amateur astronomers would be first to report, their CCD cameras trained on the sky, posting images to forums before professional observatories even finished calibrating. The global community would scan those raw frames, pixelated but powerful, looking for the comet's ghostly outline. In this way, discovery was not limited to the elite. The first whispers of Atlas's fate could come from anyone with a telescope and patience. Then would come the spectra. Professional facilities, Subaru in Hawaii, VLT in Chile, Keck on Mauna Kea, would lock onto the target and split its light into lines. Here, the receipts would appear. If carbon dioxide still dominated, survival was confirmed. If water surged forward, transformation had occurred. If the spectrum flattened, fading into noise, fragmentation was certain. These fingerprints, recorded in jagged graphs, would spread across research teams and into the public domain, each one a revelation. The blackout would end, not in silence but in data, hard and undeniable, the kind of truth that speculation could never match. The broader meaning was not lost on anyone. Atlas was not just a comet, it was an ambassador of chance, a visitor carrying the chemistry of another star's nursery. Its reappearance would teach us not only about its own structure, but about the diversity of planetary systems across the galaxy. Survival would imply that interstellar comets can endure long journeys intact, preserving their alien signatures across eons. Fragmentation would suggest fragility, a vulnerability that erases much of their story before we can read it. Transformation would offer the richest tale of all, a body layered with epochs, revealing different chapters depending on how deeply the sun burns. Each outcome was a lesson, and each lesson expanded the boundaries of what we thought possible. For the public, December promised catharsis. After weeks of rumor and doubt, there would finally be an answer. The images would fill headlines, the spectra would ripple across feeds, and the words "Atlas survives" or "Atlas lost" would trend worldwide. Some would feel relief, others disappointment, but all would feel awe. Because the return of Atlas, whatever its state, would remind us that the universe is not a silent backdrop. It is a stage where drama unfolds, sometimes hidden, sometimes revealed, always real. We cannot control the script, but we can witness it. And in witnessing, we become part of it. As December nights lengthened, telescopes warmed their sensors, amateurs cleaned their lenses, and scientists refreshed their models. Everyone was waiting for the same moment, the first confirmed sighting of Atlas after perihelion. That moment would not end the story, it would begin the next act. Because after blackout comes revelation, after silence comes data, after waiting comes truth. And the truth of Atlas survivor, ghost, or transformer would shape not only our understanding of comets, but our sense of the universe itself. Silence is not always a conspiracy. Sometimes it is a procedure. That distinction matters, especially in the strange weeks after Atlas slipped into the sun's glare. In the absence of nightly updates or official commentary, social media filled the gap with speculation. They must be hiding something, some wrote. Others hinted at military secrecy, a cover-up, a cosmic threat suppressed. But the truth is far less theatrical. The silence of institutions is not proof of deception. It is evidence of caution. In fact, when you study how agencies like NASA, ESA, or JPL operate, you realize that silence is the most predictable, even the most responsible, reaction when the data goes dark. These organizations are not built to speculate. Their internal culture is not say it first but say it right. A misstatement can damage trust for years, sometimes for entire careers. Consider how carefully even small discoveries are worded. Possible detection, preliminary results, requires confirmation. That is the vocabulary of institutions trained to avoid error. In this world, silence is often safer than a guess. And in the case of Atlas, the choice was obvious. The comet had vanished behind the Sunday. No new observations could be made until December. Any statement about its fate, whether it survived, fragmented, or transformed, would have been guesswork. Guesswork is not only discouraged, it is unacceptable. An individual researcher can speculate in a hallway or even in a podcast interview. An agency cannot. Its voice carries the weight of authority, and with that weight comes responsibility. To remain silent in such a moment is not concealment, it is discipline. This discipline is rooted in what communication experts call error aversion culture. The idea is simple. One wrong statement can erode public confidence more than 100 cautious ones can build it. Scientists know this. Administrators know it even more. When Voyager detected anomalies in the outer planets, NASA did not rush to label them. When Mars missions glimpsed strange streaks on slopes, agencies spoke in cautious tones. Recurring slope lineae, not liquid water. These choices frustrate audiences who crave headlines, but they protect credibility, which is the lifeblood of long-term science. Atlas fell into the same logic. Better to say nothing in October and November than to risk a word in error. To the public, however, silence feels like a void. And in our media culture, voids are quickly filled. Commentators spin stories. YouTubers upload theories. Headlines frame absence as secrecy. Why won't they tell us what's happening? The irony is sharp. The very silence that protects truth is reframed as evidence of lies. This is the paradox of institutional communication in the 21st century. The more careful you are, the more suspicious you look. The more disciplined your restraint, the more it is read as deception. Atlas became a mirror for this paradox. Scientists said little, because little could be said responsibly. Conspiracy culture filled the silence with noise. But step back, and the logic becomes clear. Silence in science is not evasive, it is conservative. It is the refusal to substitute rumor for receipts. For institutions, every statement must survive peer review, cross-checks, and internal committees. That process takes time. It can feel glacial compared to the viral churn of news cycles. But in the long run, it is what preserves trust. When NASA or ESA finally does speak, the public knows the words are not guesswork. They are receipts, verified and re-verified. That assurance is worth the wait, even if the wait is maddening. So the silence around Atlas, far from being proof of conspiracy, was proof of caution. Institutions were not hiding a cosmic threat. They were respecting the limits of what they could confirm. That restraint may frustrate curiosity, but it also protects truth. In the long arc of discovery, that protection is more valuable than the fleeting thrill of speculation. Silence was not absence. It was a responsibility, uncomfortable, easily misunderstood, but essential. The instinct towards silence is not paranoia. It is protection, learned through hard lessons. Science has a long memory of moments when speculation leapt ahead of data, and credibility paid the price. That is why the culture of error aversion runs so deep. Institutions prefer to wait rather than risk a wrong word, because they know history judges errors more harshly than delays. One of the oldest examples comes from the late 19th century, when astronomer Percival Lowell announced his observations of canals on Mars. At the time, telescopes were limited, and faint linear features tricked the human eye. Lowell built an elaborate narrative of intelligent Martians constructing vast waterways. Newspapers loved it. The public was enthralled, but when better telescopes proved the canals were optical illusions, credibility collapsed. It took decades for planetary science to recover from the stigma of that mistake. The lesson was clear. A single sensational claim, once proven false, can shadow an entire field. Fast forward to 2010, when NASA held a press conference teasing a discovery that will impact the search for life beyond Earth. The announcement turned out to be a claim of bacteria that could incorporate arsenic into their DNA. The media headlines were explosive. Alien biochemistry found on Earth. But within months, independent labs debunked the results. The backlash was brutal. Critics accused NASA of overselling, the public felt misled, and the phrase arsenic life became shorthand for premature hype. A decade later, scientists still cite that episode as a cautionary tale of why it is safer to say nothing until the receipts are airtight. Another wound came in 2014, when the Bicep 2 experiment in Antarctica claimed to have detected primordial gravitational wave signals from the first moments of the Big Bang. Headlines called it the discovery of the century. Nobel predictions flew. But follow-up analysis showed the signal was contaminated by galactic dust. The triumph evaporated, leaving embarrassment in its place. No fraud, no malice, just premature certainty. Still, the cost was the same. Public trust bruised, reputations dimmed. Institutions like NASA and ESA carry those scars. They know how easily excitement can become disillusionment when patience is abandoned. Even smaller cases reinforce the lesson. In 1993, a misinterpretation of images from the Phobos 2 spacecraft led to claims of an artificial monolith on Mars's moon. The media ran with it. Scientists spent years clarifying that it was a natural boulder. By then, the damage was done. Conspiracy theories thrived, fueled by the premature wording. The same dynamic repeats with every ambiguous anomaly. A cautious phrase, possible detection, is defensible. A bold headline, proof of life, is not. This is the cultural backdrop to Atlas. When the comet vanished into solar glare, agencies faced a choice. Speculate publicly about survival, fragmentation, or transformation, or say nothing until December. History made the choice easy. Better to endure accusations of secrecy than to risk repeating Lowell, or arsenic life, or Bicep 2. Error aversion is not cowardice. It is institutional memory at work. It is the understanding that credibility is fragile, that once broken, it may never fully return. Silence, uncomfortable as it is, preserves the one resource more valuable than data: trust. For the public, this can feel unsatisfying. Silence does not feed curiosity. It does not trend on social media. But institutions play a different game. They are not judged by likes or shares. They are judged by accuracy, by whether their words withstand the test of time. That is why, in the Atlas case, restraint was the dominant strategy. It may look dull compared to speculation, yet in the long view, it is the only path that honors both science and the public who depends on it. One of the easiest mistakes the public makes is to blur the line between science and security. When institutions fall quiet, some assume it must mean danger, perhaps even government cover-up, but history and practice tell a different story. If Atlas or any interstellar object posed an actual threat to Earth, the silence would not deepen, it would shatter. Military posture would change in ways visible, even to the casual observer. Silence belongs to science. Security speaks in signals. Consider how defense networks operate today. NORAD tracks objects entering Earth's atmosphere with radar sweeps that run 24 hours a day. U.S. Space Command monitors catalogs of orbital debris and new entrants, coordinating with allies in Europe and Asia. NASA's Planetary Defense Coordination Office runs regular simulation exercises, publishing their scenarios openly. Asteroid strikes, impact probabilities, mitigation strategies. These systems are designed not only to detect but to broadcast threats. If Atlas had been on a collision trajectory, the signals would have been everywhere: alerts issued, press briefings scheduled, telescopes mobilized, even military assets readied. Governments cannot keep such a posture invisible. It shows up in budgets, satellite tasking, and the movements of hardware. Secrecy is impossible in a world where amateurs with backyard telescopes can verify orbits. The absence of such a posture during Atlas's approach was itself the clearest evidence. The comet was never considered a threat. The contrast with real alerts is instructive. In 2022, when asteroid 2021 QM1 briefly looked like it might intersect Earth's orbit in 2052, NASA issued updates, ESA tracked it, and the story ran in newspapers. The impact probability was tiny, but the culture of planetary defense demanded openness. Agencies explained the numbers, clarified the risk, and published the receipts. Or in 2019, when asteroid 2006 QV89 appeared in near-term risk lists, similar procedures followed. Threats, even small ones, generate noise because ignoring them would be catastrophic to trust. Atlas generated no such noise. Its trajectory was extraordinary. Yes, but extraordinary is not the same as dangerous. This difference between science and security is critical. Science goes silent when uncertain. Security goes loud when threatened. In the case of Atlas, science was uncertain, hence the quiet. But security was unconcerned, hence the absence of posture. No emergency budgets, no sudden telescope reallocations, no DoD pressers, no NATO consultations. Silence in both domains was not evidence of danger. It was evidence of normalcy. The comet's path was unusual, but unusual geometry is not a national security issue. It was a research subject, not a defense scenario. Still, speculation thrives in ambiguity. Comment threads and late-night podcasts blurred the two silences, scientific caution mistaken for security secrecy. If nothing was wrong, why say nothing? The logic goes. But the premise is flawed. In reality, institutions do speak when danger exists. The very absence of those signals is a form of communication in itself. It says, there is no threat here, only curiosity. That distinction may not satisfy the appetite for drama, but it reflects the truth. Atlas was extraordinary in science, not in security. And the silence of both domains was not collusion but coincident, science waiting for data, security seeing no danger. Understanding this helps the public resist the gravitational pull of sensationalism. Not every pause is a plot, not every gap is a secret. Sometimes, a comet is just a comet, strange, fascinating, alien in chemistry, but not hostile. And in that recognition lies a calmer wonder. The knowledge that the universe can be mysterious without being menacing, and that silence does not always hide catastrophe. Sometimes, it simply means there is nothing catastrophic to hide. The real lesson of Atlas's silence is that not all silence is equal. In the echo chambers of online speculation, every pause becomes a plot. But inside institutions, silence is often the loudest form of responsibility. To speak prematurely would mislead. To speak irresponsibly could misinform. Choosing restraint is not weakness but strength. It is the discipline of organizations that know their credibility is harder to repair than it is to preserve. And in the case of Atlas, that discipline mattered more than drama. Think of the difference in incentives. Media thrives on immediacy. A headline delayed is a headline lost. Social platforms thrive on sensation. A theory that excites spreads faster than a fact that waits. Institutions, by contrast, thrive on durability. Their credibility must outlast news cycles, outlast rumors, outlast even the lifespans of missions. This is why the voice of NASA or ESA sounds flat compared to the pulse of speculation. Their silence is not a failure to engage, it is fidelity to a different timeline, the timeline of evidence, not excitement. In that sense, reticence is not a bug in institutional culture. It is the feature that protects science from collapsing under the weight of its own hype. Critics sometimes argue that this reticence feeds conspiracy by leaving space for it. There is some truth there. Vacuums invite noise. But the alternative is worse. Imagine if agencies speculated publicly about Atlas's fate in November, suggesting survival 1 week, fragmentation the next, transformation the week after. Each reversal would erode trust. By December, when the data finally arrived, the public would be less willing to believe it. Speculation corrodes confidence. Silence preserves it. The temporary frustration of waiting is preferable to the permanent damage of contradiction. This is why institutions hold back. They know the danger of feeding the rumor mill is greater than the discomfort of letting it spin unchecked. The same applies to security. If Atlas had been a threat, the signals of posture would have been unmistakable radar alerts, defense briefings, contingency planning. None of those occurred. That absence was not suspicious. It was clarifying. The comet was not dangerous, and so defense remained silent. Conspiracy culture reads absence as presence. If they're not saying anything, something must be wrong. But reality is simpler. Sometimes the absence of an alarm is evidence of safety. Sometimes quiet is the clearest signal of all. Seen in this light, institutional reticence is not a wall between the public and truth. It is a guardrail that keeps truth from being diluted by noise. It frustrates curiosity in the short term, but it preserves clarity in the long term. It is the difference between a science that lasts and a science that burns itself out chasing headlines. In the Atlas story, that distinction became clear. The silence of October and November was not a conspiracy. It was character. And character, in the end, is what sustains institutions through both discovery and doubt. But here lies the irony. While institutions stayed quiet, the media environment grew restless. For the public, the gap between silence and speculation felt intolerable. Where official voices paused, unofficial voices filled the air. And so the next chapter of Atlas's story is not only about data or science, it is about perception. It is about how silence is read, how unease is amplified, and how trust can fray in the spaces where communication falters. That is the bridge from institutional reticence to public unease, the very terrain we must now cross. Whispers travel faster than receipts. In the first week of November 2025, with Atlas hidden behind the sun and the scientific community forced into silence, a rumor began to spread. It did not start with a press release or a research paper. It began with vague mentions on blogs and half-sourced social media posts that senior officials from multiple U.S. agencies had converged on Quantico, Virginia, for a high-level meeting. Quantico, the training ground of the FBI, the Marine Corps, and other federal institutions, already carried an aura of secrecy in the public imagination. Add the timing, just days after Atlas vanished into the solar glare, and the narrative practically built itself. What else could it be about? People asked online. Headlines followed. Atlas Summit at Quantico? Podcasts speculated about national security briefings. In a media environment already primed by silence, the story gained traction without ever producing evidence. But here is the key fact. There is zero public evidence connecting Atlas to any such meeting. The rumor was built on fragments, not receipts. A leaked travel manifest showed officials flying into Virginia. A line item on an internal schedule mentioned closed briefing. An unnamed source described urgent interagency discussions. None of these fragments mentioned space. None mentioned comets. None tied the event to Atlas in any way. And yet, in the weeks of blackout, the absence of clarity was enough for the story to metastasize. The dots were connected not by documents but by imagination. The comet was invisible. The officials were meeting, therefore the meeting must be about the comet. It was a story of timing, not of truth. Investigative reporters tried to chase it down. Outlets from the Washington Post to smaller science blogs made inquiries. Yes, there was a meeting at Quantico in early November. That part was real, but such meetings are routine. Quantico hosts end-of-year training audits, budget reconciliations, interagency counter-terrorism workshops, and even cybersecurity exercises. In an ordinary year, the event would have passed without a headline. Only because it coincided with Atlas's blackout did it draw attention. Sources familiar with the agenda mentioned fiscal deadlines and interdepartmental coordination. Not one cited comets, astronomy, or planetary defense. To serious journalists, the leap from meeting to Atlas was unsupported. To the rumor mill, that very absence of detail became fuel. This dynamic reveals a paradox of perception. Silence in science, as we saw in Part 7, stems from error aversion. Better to say nothing than to risk a wrong word. Silence in security stems from confidentiality. Better to say little than to compromise an operation. When both silences occur together, they are easily conflated. To the outside eye, it looks like synchronization. In reality, they are coincidental. Two separate rhythms overlap in time. But when the public is primed by suspicion, coincidence feels like conspiracy. A comet goes dark, officials meet, therefore the two events must be linked. Yet, the absence of receipts is itself the strongest receipt. No public evidence means no confirmed connection. Correlation is not causation. Timing is not intent. Silence is not proof. What gives this rumor power is the symbolic weight of Quantico. For decades, it has been shorthand in American culture for secrecy, law enforcement authority, and classified briefings. A budget meeting at Quantico is just a budget meeting, but once framed by the name alone, it sounds clandestine. That symbolic resonance made it irresistible during Atlas's blackout. It offered a concrete stage onto which cosmic anxieties could be projected. The human mind prefers a narrative, and Atlas meeting at Quantico provided one when no other story was available. Journalists who resisted the pull of speculation emphasized the void. There were no comet references in the agenda, no planetary defense experts flown in, and no coordination with NASA or ESA reported. A genuine Atlas crisis would have drawn in astronomers, not just law enforcement officials. A genuine planetary defense posture would have triggered visible signals, radar sweeps, Space Command notices, even NASA press coordination. None of that occurred. The Quantico meeting was real. The Atlas connection was imagined. And yet, the imagined link spread faster than the mundane truth. That, more than anything, illustrates the media landscape of 2025. Whispers travel faster than receipts, especially when receipts are dull and whispers are dramatic. The result was predictable. For some, the meeting became evidence of a cover-up. For others, it was a symbol of institutional secrecy. For a few, it was proof that Atlas was being discussed at the highest levels. But for those willing to hold a stance of healthy skepticism, the conclusion was simpler. Extraordinary claims require extraordinary evidence, and in this case, there was none. Without receipts, the story collapses. The blackout of Atlas created space for speculation. The coincidence of a routine meeting filled that space, and the rumor of Quantico became a mirror of our own hunger for meaning in moments of silence. Rumors move faster than evidence because they require less fuel. Evidence needs receipts, documents, names, timestamps, and corroboration. Rumors need only timing and imagination. In the blackout weeks of Atlas, the rumor about Quantico had both. It landed in a moment when the world was already restless, when scientists refused to speculate, when telescopes produced no images. In that vacuum, almost any fragment could take root. A meeting, a calendar note, a rumor of officials traveling, that was enough to seed a story. And because humans are pattern-seeking, the pattern was irresistible. Atlas goes dark. Officials meet. Therefore, the officials must be meeting about Atlas. This is how information vacuums work. When institutions remain cautious, the space left empty is not truly empty. It is filled by narratives. Social platforms accelerate the process. An anonymous post claiming briefings at Quantico spreads faster than a sober reminder that meetings happen every week. Headlines amplify the framing, not meeting at Quantico, but Atlas, meeting at Quantico, the question mark doing the work of confirmation. Audiences already primed by suspicion interpret silence as concealment. In such conditions, speed trumps accuracy, and speculation metastasizes before facts can catch up. That is why, by mid-November, more people online had heard about the Quantico Atlas Summit than had read the official ESA technical bulletins. Whispers travel faster than receipts because they are cheaper to produce, easier to share, and emotionally more satisfying. Investigative reporters who tested the rumor found no receipts, no astronomers on travel manifests, no coordination with NASA, ESA, or the Planetary Defense Coordination Office, no mention of comets in any agenda. The meeting existed, the connection did not. In journalistic language, this is called zero public evidence, and that phrase matters. It does not deny the possibility of hidden links, it simply notes the absence of anything verifiable. Without receipts, a story collapses. Yet in today's media ecosystem, the absence of receipts is often reframed as evidence of a cover-up. If nothing is there, why not show us? This inversion flips the burden of proof. Instead of demanding evidence for extraordinary claims, it demands proof against them. That reversal is the lifeblood of conspiracy culture, and it played out perfectly in the Quantico rumor. History shows the pattern repeating. During the COVID pandemic, gaps in data about vaccine side effects were quickly filled by speculation, often traveling faster than peer-reviewed updates. When the Pentagon declassified videos of unidentified aerial phenomena in 2020, the absence of a detailed explanation was read as confirmation of extraterrestrial craft. When Edward Snowden revealed classified surveillance in 2013, the lack of official comment fed narratives wilder than the receipts themselves. In each case, silence or delay magnified suspicion. The rule is simple: the less information offered, the more imagination fills the gap. And imagination, unbounded by receipts, always runs faster. Atlas and Quantico followed that script. The comet went dark, scientists refused to speculate, and a meeting at a symbolic site offered the perfect canvas. No evidence tied the two, but the very absence of connection was turned into a connection. By mid-November, YouTube channels were offering hour-long dissections of secret planetary defense discussions. Podcasts treated the meeting as an ominous clue. Tweets framed it as a smoking gun. Meanwhile, the receipts remained blank. No documents, no confirmations, no scientists in attendance. Just a narrative inflated by timing and repetition. Healthy skepticism means holding both truths at once. The meeting happened, and the comet vanished. But there is no public evidence connecting them. That stance resists both extremes: the naivete of dismissing patterns outright, and the paranoia of accepting them without receipts. It is the middle ground that journalism and science both demand. By reminding ourselves of zero public evidence, we protect against the gravitational pull of narrative. We anchor in what is verifiable, even if it is less dramatic than rumor. And in the Atlas story, that anchor is essential, because without it, every coincidence becomes a conspiracy, and every silence becomes a secret. When journalists pressed for details about the Quantico meeting, the answers were not cosmic at all, they were bureaucratic. The timing in early November coincided with the annual cycle of federal planning, fiscal years in the U.S. government close on September 30th, and October and November are always crowded with reviews, reconciliations, and interagency briefings. Quantico is one of several hubs where such work occurs. Meetings about resource allocation, law enforcement budgets, and year-end performance assessments often spill into November. To those who follow government rhythms, the timing was not mysterious, it was predictable. But to audiences primed by Atlas's blackout, predictability looked like a conspiracy. The mundane explanation never travels as far as the dramatic one. Personnel rotation was another factor. Fall is a common season for leadership changes. New directors confirmed, senior staff reassigned, task forces reshuffled. Quantico hosts many of these transitions, particularly for FBI and interagency programs. A briefing labeled closed can easily mean nothing more than a change of command or an internal audit. In fact, sources later confirmed that one part of the November agenda involved counter-terror training modules and cybersecurity initiatives, both recurring programs. Again, nothing in the receipts pointed to comets, but in an atmosphere charged by Atlas speculation, closed briefing became shorthand for cosmic secrecy. The leap from HR to interstellar visitor is vast, but rumor requires only timing, not logic. Geopolitics also played its role. The fall of 2025 was not quiet on the world stage. Intelligence agencies were grappling with cyber intrusions traced to state actors, with conflicts simmering in multiple regions, and with terrorism threats evolving online. Counter-terror coordination at Quantico is routine under such conditions. Analysts familiar with interagency scheduling noted that these gatherings often cluster near the end of the calendar year, when threat assessments are updated and budgets realigned. In that light, the November meeting looked less like a response to a comet and more like the ordinary machinery of national security. Silence was not cosmic, it was bureaucratic. The only thing unusual was the lens through which the public viewed it. Even training exercises contributed. Quantico runs scenario drills, some classified, some not, that cycle throughout the year. Participants practice response coordination, test communication systems, and rehearse crisis management. Many of these drills are deliberately kept low profile to preserve realism. In early November, one such exercise reportedly focused on domestic security vulnerabilities. Again, nothing about comets, nothing about Atlas, but when details are sparse, imagination supplies the missing words. Closed exercise becomes secret summit. Annual audit becomes planetary defense. The process is less about deceit than about projection. The public fills gaps with the story it already expects. Healthy skepticism means recognizing these mundane explanations. The Quantico meeting did not occur in a vacuum. It occurred in the familiar context of fiscal deadlines, personnel rotations, geopolitical assessments, and training cycles. These are receipts, even if less glamorous than whispers, and they remind us of a broader truth. Not every closed door hides an extraordinary secret. Sometimes it hides paperwork. Sometimes it hides staffing charts. Sometimes it hides nothing at all beyond the ordinary work of government. To mistake routine for revelation is to flatten reality into drama, and that does no service to either science or the public. In the Atlas case, connecting the comet to Quantico says more about our hunger for narrative than about the facts themselves. The comet was real, the blackout was real, and the meeting was real, but the leap between them lacked receipts. Zero public evidence connected the dots, and in the discipline of journalism, as in science, the absence of evidence is decisive. It does not prove absence, but it demands humility. Without receipts, we cannot claim a connection. The healthier posture is to remain skeptical, curious but cautious, aware of coincidence but not enslaved by it. Because if every coincidence becomes a conspiracy, we lose the ability to distinguish signal from noise. The real strength of science is not in the answers it protects, but in the questions it is willing to kill. That is the spirit with which astronomers entered the final stretch of 2025, waiting for Atlas to emerge from the sun's glare. After months of speculation and silence, the task ahead was not to cling to favorite narratives, but to test them, rigorously and ruthlessly. In professional terms, researchers spoke of building a hypothesis bank. Like a vault, it stored the possible explanations for Atlas's strange behavior, some simple, some extraordinary. Each hypothesis came with rules for verification and rules for rejection. No belief would be taken on faith. Every idea was on probation, awaiting the receipts of December. The approach is deeply rooted in the culture of scientific discipline. It is not enough to suggest that Atlas is unlike any comet we've seen. That phrase excites the public but paralyzes inquiry. Instead, scientists map the anomalies into categories, create measurable predictions, and then ask, how could this idea be falsified? In other words, what observation would kill it? A hypothesis that cannot be killed is not science, it is myth. By late 2025, 3 main hypotheses dominated the Atlas file, each paired with a plan for falsification. The task was simple in principle, brutal in practice: put every story at risk and see which one survives the data. Why is this important? Because the temptation, in moments of mystery, is to build narratives that resist correction. Atlas's bizarre chemistry and erratic brightness make it a perfect canvas for speculation: alien chemistry, interstellar artifact, cosmic omen. But speculation without falsification is quicksand. The hypothesis bank method keeps the field solid. It does not dismiss imagination, it disciplines it. It says, dream boldly, but then design the receipts that could destroy your dream. If your idea survives the test, it grows stronger. If it fails, it falls away, leaving clarity in its place. This discipline was especially urgent for Atlas because of its CO2 divided by H2O anomaly. A ratio of roughly 8:1, with carbon dioxide outshining water vapor, is not just unusual, it is unprecedented for comets observed in our system. Some argued it must mean Atlas is fundamentally CO2 dominant, perhaps forged in a colder, carbon-rich nursery around another star. Others suggested it meant a layered nucleus, CO2, rich ices on the surface, hiding deeper reservoirs of water ice that would only reveal themselves after perihelion. A third camp focused on dust, proposing that geometric effects like an anti-tail were distorting our measurements. Each idea had defenders, each idea had weaknesses, and all were written into the hypothesis bank, waiting to be judged by December skies. The discipline of falsification meant every hypothesis was paired with a test. If Atlas survived perihelion and CO2 continued to dominate, the CO2 comet model would gain ground. If water surged, the layered nucleus model would rise. If dust geometry explained the odd tail, the anti-tail theory would win. And if none matched, a new page would be opened in the bank, a reminder that science is always provisional. By structuring the conversation this way, scientists insulated themselves against both hype and despair. Whatever December revealed, it would not be chaos. It would be a test, and tests bring clarity. This framework also offered a lesson to the public. Mystery does not mean absence of method. Silence does not mean absence of work. Behind the scenes, astronomers were not idly waiting. They were preparing receipts in advance, sharpening the knives of falsification. They knew that when Atlas returned, the world would look for answers. They were ready to deliver, not guesses, but tested ideas. That is the heartbeat of scientific discipline. Not certainty, but readiness to be corrected. Among the hypotheses stored in the Atlas bank, the boldest and simplest was this: maybe Atlas really is what it appears to be, a comet dominated by carbon dioxide. No hidden layers, no geometric tricks, just an interstellar body whose chemistry is fundamentally different from anything native to our solar system. The argument for this view was straightforward. Every observation before perihelion showed CO2 lines dwarfing H2O by a factor of about 8:1. Other comets, even when unusually rich in carbon compounds, rarely exceed a 1:1 ratio. Atlas did not flirt with anomaly. It lived in it. Perhaps that anomaly was not a surface quirk, but the essence of the object itself. Testing this hypothesis required patience. The key prediction was clear. If Atlas remained CO2 dominant after perihelion, the model would hold. Instruments like NOMAD and ACS aboard the trace gas orbiter, as well as ground-based spectrographs, would be able to compare pre- and post-perihelion spectra. If the ratio stayed consistent, the CO2 comet explanation would survive another round. If water vapor suddenly surged, the hypothesis would collapse. It was a clean test, which is why many scientists favored it. Falsification was simple. A change in ratio would kill the idea. In the discipline of science, the simplicity of the kill test was a strength. Why might Atlas be so CO2 rich? One explanation pointed to its birthplace. In our own solar system, volatiles like water freeze closer to the sun than carbon dioxide, which requires colder temperatures to condense. A body rich in CO2 but poor in H2O would therefore have formed in a region far beyond our Kuiper belt, an interstellar nursery where carbon dioxide ice was plentiful and water scarce. If Atlas retained that chemistry across light years, then we were holding in our telescopes a direct sample of conditions around another star. That possibility electrified planetary scientists. It meant the diversity of cometary chemistry across the galaxy might be wider than we imagined. Earth's solar system would be only one example among many, not the template. Still, the simplicity of the hypothesis carried a risk. It could be too simple. Detractors noted that comets often surprise us, and surface chemistry does not always represent the bulk interior. A veneer of CO2 could fool instruments until deeper layers are exposed by heat. But defenders countered, sometimes what looks simple is true. Extraordinary claims are not always the ones that overturn appearances. Sometimes they are the ones that accept appearances at face value. If Atlas looked like a CO2 comet before perihelion and looked the same after, perhaps it really was one. Falsification would decide. The implications of confirmation would be profound. A validated CO2 dominant comet would show that interstellar chemistry is not only possible but stable across eons of travel. It would tell us that planetary systems can produce bodies utterly unlike our own, preserving their identity across light years. For astrobiology, the lesson would be sobering. Not every system will produce water-rich comets like those that delivered oceans to Earth. Some will deliver carbon dioxide instead, with very different implications for habitability. Atlas could thus be a messenger, not of life, but of limits, the reminder that not every star births an Earth. And yet, even here, wonder survives, because if science is disciplined enough to test and kill weak ideas, it must also be open enough to accept strong surprises. If Atlas truly is a CO2 dominant comet, we are watching chemistry from another star's nursery blaze across our sky. That outcome may not feed conspiracy theories or mystical metaphors, but it feeds something deeper, the recognition that the galaxy is wider, stranger, and more diverse than we ever imagined. The second hypothesis in the Atlas bank was subtler, but to many scientists more plausible. The comet's nucleus was layered. According to this model, the anomaly of an 8:1 CO2A to H2O ratio was not evidence of a fundamentally carbon-rich body, but of a stratified structure. In other words, what we were seeing before perihelion was simply the surface story. Carbon dioxide ices, more volatile than water, were the first to sublimate when sunlight reached the comet. That venting dominated early spectra, but beneath those layers lay deeper deposits of water ice. If so, perihelion would act like a blowtorch, burning through the outer crust and exposing a new chapter of chemistry. After October 30th, Atlas would no longer look like a CO2 comet. Its signature would pivot toward water. This hypothesis was rooted in well-established comet physics. On Earth, dry ice, frozen CO2, sublimates at temperatures where water ice remains solid. The same principle applies in space. As a comet approaches the sun, CO2 turns to gas first, jetting outward through cracks and vents. Only when solar heating penetrates deeper does water vapor begin to dominate. In solar system comets, we see this layering effect often. Early outbursts are driven by CO2 or CO, while later activity is increasingly water-rich. What made Atlas unusual was the sheer imbalance, an 8:1 ratio, far beyond typical ranges. But instead of rewriting the laws of chemistry, the layered model suggested we were witnessing an extreme version of a familiar process. Testing the layered nucleus hypothesis required careful monitoring across perihelion. The prediction was precise. The CO2 divided by H2O ratio should shift significantly by December. Spectra collected by instruments like NOMAD, ACS, or Earth-based observatories would reveal whether water lines surged in intensity. A move from 8:1 toward 2:1, or even parity at 1:1, would confirm the hypothesis. Conversely, if the ratio held steady, the layered model would collapse, leaving the CO202 comet theory stronger. This made the hypothesis scientifically healthy. It risked falsification. Its advocates knew exactly what receipts would kill it, and they welcomed the test. The implications of confirmation would be profound. A layered nucleus would mean Atlas is not a monolithic oddity but a complex archive. Each stratum would preserve conditions from different epochs of its birth environment. The outer layers, rich in CO2, might reflect a cold carbon-heavy phase of its protoplanetary disk. The deeper layers, rich in water, might reflect a warmer or more mixed phase. In effect, Atlas would be a time capsule with multiple chapters, an interstellar Rosetta Stone, preserving not just one chemistry but a sequence of chemistries. For planetary science, that would be gold. It would show that interstellar comets can encode layered histories, making them richer messengers than we ever hoped. The layered model also carried a philosophical appeal. It fit the narrative of revelation, of mystery yielding to depth. Atlas's surface story was dramatic but incomplete. Perihelion was the turning point, the peeling back of a mask. If water surged in December, it would confirm the lesson. What lies beneath is often different from what lies above. And for a public hungry for story, that resonance was powerful. Science would not only explain but also enrich the metaphor that the cosmos holds, layers, and truth emerges by burning through illusion. Of course, if the ratio did not change, the hypothesis would fall. That was the discipline at its core. Advocates of the layered model accepted that failure was possible, even likely. They knew the risk, but they also knew the reward. If Atlas pivoted to water, their framework would stand as the most elegant explanation, and if not, the falsification itself would sharpen science, clearing the bank of a story that no longer fits. That is the beauty of the method. Every test, win or lose, is a step toward clarity. The third hypothesis in the Atlas bank was less about chemistry and more about geometry. According to this model, some of the comet's strangest signatures might not be intrinsic at all, but artifacts of dust dynamics. The key suspect was the so-called anti-tail phenomenon, a rare optical effect in which a comet's dust tail appears to point toward the Sun instead of away from it. This illusion arises from perspective. When a comet's orbit crosses the plane of Earth's line of sight, dust grains spread along its orbital path can appear as a narrow spike against the solar wind. To the eye, and sometimes to instruments, the geometry creates anomalies that mimic exotic physics. What looks like alien behavior may simply be alignment. Atlas, with its eccentric trajectory hugging near the ecliptic, was a prime candidate for such tricks. As Earth's vantage point shifted in late 2025, some observers noted that its tail morphology did not behave as expected. Brightness fluctuations, odd orientations, and even misleading spectra all could have been distorted by dust geometry. The anti-tail hypothesis suggested that part of the CO2 divided by H2O puzzle might not be chemistry at all but optics. Dust scattering sunlight in unusual ways, contaminating the gas lines in spectra. Before invoking alien chemistry, the argument went, one must exhaust the possibility of geometry. Testing this idea required precise measurements. The prediction was that as Atlas reappeared in December, changes in Earth's viewing angle would alter the apparent anomalies. If brightness ratios shifted with geometry rather than solar heating, that would be evidence for an anti-tail. Instruments would need to measure the phase angle, the angle between Sun, comet, and Earth, while simultaneously capturing dust spectra. If anomalies lined up with geometry rather than perihelion timing, the anti-tail hypothesis would gain strength. Conversely, if anomalies persisted regardless of viewing angle, the model would collapse. The falsification criteria were as clear as the comet's orbit. History lent credibility to the idea. In 1957, comet Aaron Rowland startled astronomers with a spectacular anti-tail, leading to confusion and speculation until geometry explained the effect. More recently, comets like Hale-Bopp and Ison displayed dust features that misled early interpreters. Each case became a cautionary tale. Never mistake optics for ontology. The cosmos can fool the eye, and sometimes the spectrograph. By late 2025, many researchers remembered those lessons. Perhaps Atlas's strangeness was not chemistry beyond imagination, but perspective beyond intuition. Still, the anti-tail hypothesis faced skepticism. Could dust geometry alone account for an 8:1 CO2H2O ratio? Critics doubted it. Gas lines in spectra are harder to fake than brightness curves. Dust can contaminate readings, but it rarely overwhelms them. Proponents acknowledged the limits. The antitail might not explain the entire anomaly, but it could explain part of the noise, especially the erratic light curve. Atlas's flickering could be less about chemistry and more about clumps of dust catching sunlight at odd angles. Even a partial correction would matter. It would separate true chemical mystery from geometric distraction. The implications of confirmation would be humbling. If geometry explained much of Atlas's behavior, the story would shift from alien chemistry to familiar optics. That would not diminish the comet's value, it would sharpen it. By subtracting illusion, science would isolate what was genuinely new. Antitail confirmation would remind us that even in the era of Hubble and JWST, perspective still tricks us. The cosmos is not always strange. Sometimes we are simply looking at it strangely. And yet, humility itself is a kind of wonder. If Atlas teaches us that anomalies can vanish when geometry is accounted for, that is still a discovery worth having. It tells us that science works, that discipline can strip away illusions, leaving a clearer view, and if, after stripping geometry away, anomalies remain, then we know they are real. Either outcome is progress. That is why the antitail sat in the hypothesis bank beside its rivals, awaiting December's receipts. No hypothesis bank is complete without a drawer labeled wildcard. Scientists, trained by history, know that the cosmos often refuses to fit our categories. We design models, we sharpen falsification tests, but then reality hands us something else entirely. To deny that possibility would be arrogance. To prepare for it is discipline. With Atlas, the wildcard slot was not a luxury. It was a necessity. The comet had already broken rules with its CO2 anomaly and erratic light curve. It might yet break more. What would a wildcard look like? It could be fragmentation so complete that none of the three main hypotheses survives. Instead of CO2 dominance, layered nucleus, or dust geometry, Atlas might emerge in December as a cloud of dust, its nucleus destroyed, its chemistry unreadable. That outcome would collapse the hypothesis bank, not by falsification within categories, but by erasing the subject itself. Or the wild card could move in the opposite direction. Atlas could reveal chemistry beyond both CO2 and H2O, with unexpected volatiles dominating its spectra: methanol, ammonia, or something unimagined. In that case, the anomaly would deepen, not resolve, forcing an entirely new branch of theory. Even a trajectory could surprise us. A non-gravitational acceleration, like the one that puzzled astronomers with Oumuamua in 2017, could alter Atlas's path in ways no dust model predicts. Each of these outcomes would break the bank, but breaking is part of the process. History warns us to expect the unexpected. In 1994, comet Shoemaker-Levy 9 slammed into Jupiter, fragmenting spectacularly, an event predicted only after its discovery. In 2013, Comet Eisen, heralded as the comet of the century, disintegrated at perihelion, stunning observers who had expected a brilliant display. In 2017, Oumuamua, the first known interstellar object, defied classification: too elongated, too bright, too odd in motion. Each event reminded scientists that surprise is not an exception, but a rule. Atlas, arriving from the depths between stars, belonged in that lineage. To prepare only for the predictable would be to miss the essence of discovery. The discipline of science is not about predicting every twist. It is about preparing to falsify what can be falsified, and being willing to expand the map when falsification fails. The hypothesis bank was therefore designed with humility. It held three strong contenders: CO2 dominance, layered nucleus, antitail geometry, each testable, each killable. But it also left space for outcomes outside the frame. If December brought one of those outcomes, the bank would not collapse. It would grow, a new page would be written, and the process would begin again. That is not failure, that is method. For the public, the wild card carries a special lesson. Mystery does not mean chaos, and surprise does not mean defeat. If Atlas behaves in ways no one expected, it will not be the end of science, it will be its renewal. Each surprise extends the horizon, reminding us that the universe is not bound by our categories. The very willingness to be surprised, to admit that our models may be incomplete, is what makes science stronger than speculation. Where rumor clings to certainty, science clings to openness. Where conspiracy insists on answers, science insists on tests. The wild card is not a loophole, it is the badge of honesty. And so, as December approached, astronomers held their bank of hypotheses with two hands, one firm with discipline, the other open with wonder. They were ready to test, ready to kill, ready to confirm, but they were also ready to be surprised. That balance, rigor and humility, discipline and openness, is the essence of science. Atlas may confirm what we expect, or it may reveal what we never imagined. Either way, the hypothesis bank will not close. It will continue, page after page, as long as the cosmos has questions left to ask.